In 2025, physicists recorded a phenomenon that shatters the foundation of physical reality. A subatomic particle bypassed an impenetrable physical barrier, and the time it took to do so was precisely measured as 0. Not an approximation of the speed of light. Absolutely instantaneous. For over a century, the speed of light has been the ultimate, unbreakable law of the cosmos. But what if that speed limit only applies to the observable macroscopic universe, while the quantum realm possesses a structural backdoor we are only just learning to open? Imagine driving a vehicle toward a solid concrete wall. In the framework of classical mechanics, a collision is inevitable. The structural integrity of the wall guarantees that the vehicle will stop. But in the strict probabilistic mathematics governing the quantum domain, there is a calculated, distinct probability that you simply continue your trajectory and appear on the other side of the wall without ever passing through the space between. This is no longer an abstract mathematical model. It is an engineered reality that is unfolding in laboratories right now. We call this phenomenon quantum tunneling. To understand the gravity of this, we must strip away the classical assumptions we rely on daily. At the subatomic scale, particles do not possess a fixed location until they are measured. They exist as a cloud of probabilities, a wave function that dictates where they might be found. When an electron encounters a barrier of energy, that it technically does not possess the kinetic energy to overcome classical physics, states it must bounce back. Yet the wave function does not immediately drop to 0 at the barrier. It decays exponentially inside it. If the barrier is thin enough, a fraction of that probability wave emerges on the far side. When the electron is finally measured, there is a finite chance it is found beyond the wall. It did not climb over. It did not break through. It simply tunneled. But the profound shock of recent experiments is not that tunneling occurs. We have utilized tunneling in semiconductors and flash memory for decades. The paradigm-shifting revelation lies in the transit time. How long does the particle spend inside the barrier? Advanced attosecond measurement protocols in recent trials have isolated this transit duration, and the data reads 0. The particle is detected at the destination at the exact instant it leaves the source. It is moving from point A to point B without traversing the intervening space. It is a true, instantaneous displacement. This introduces a severe mathematical and physical paradox. If a particle can relocate in 0 time, it is effectively traveling infinitely fast. It completely ignores the cosmic speed limit of 300,000 kilometers per second, established by the behavior of photons in a vacuum. You might think this is merely a microscopic anomaly, an insignificant glitch in the cosmic hardware that has no bearing on our macroscopic reality. But recent data suggests that coded information can be transmitted through these tunneling barriers without any time delay. We are looking at the foundational mechanics of a universe that might not be as rigidly bound by distance as we have been led to believe. And if information can bypass distance, the logical progression leads us towards scaling this effect. We are witnessing the early stages of a scientific revolution that forces us to question if the vast, isolating distances between star systems are permanent walls or merely boundaries defined by our current limitations in observation engineering. The implications are staggering. If the speed of light is broken, we must immediately confront a terrifying proposition regarding the nature of time itself. Albert Einstein constructed a universe governed by strict, unyielding causality, where cause must always mathematically and physically precede effect. But superluminal tunneling forces physics into a crisis. What happens to our understanding of reality when the effect arrives before the cause? In classical relativity, the speed of light is not just the maximum velocity of an object, it is the fundamental speed of causality itself. It determines the sequence of events across the universe, ensuring that a glass shatters only after it hits the floor. If a particle tunnels through a barrier instantaneously and is observed traveling faster than light, it fundamentally disrupts this sequence. From the perspective of a moving observer, Relativity dictates that this superluminal particle would appear to travel backward in time. This is not a trick of mathematics, but a genuine physical crisis. If we can transmit a signal faster than light, we can theoretically send a message to the past. This creates paradoxes that threaten the logical structure of the universe. Yet the empirical data from the 2025 tunneling experiments remains resolute. The transit time is zero. The particle simply does not spend time traversing the barrier. How do we reconcile this? Theoretical physicists are currently locked in intense debate. Some argue that while the particle appears to tunnel instantly, we cannot use this phenomenon to transmit usable information faster than light, because the tunneling process itself is governed by strict quantum probability and randomness. You cannot predict which specific particle will tunnel successfully, making reliable superluminal communication impossible. However, this defense mechanism of causality is currently under severe attack. Recent breakthroughs in quantum optics and signal processing have demonstrated the preliminary transmission of coherent datasets through tunneling barriers utilizing vast ensembles of particles. While individual particles remain unpredictable, the statistical behavior of the ensemble allows for error-corrected data reconstruction on the other side. We are learning to force a signal through the quantum back door. This shifts the debate from whether instantaneous travel is possible to whether the universe will allow us to harness it macroscopically. If we can encode data into a probability wave and reconstruct it instantly on the other side of an energy barrier, we have bypassed the structural limits of space. Imagine the immediate applications. A communication network completely free of latency spanning millions of kilometers, controlling rovers on distant moons in real time. But the ambition of current research extends far beyond telecommunications. We are now investigating the Hartman effect scaling, which presents an even more profound anomaly. I once assumed that the thicker a physical barrier, the slower any penetrating object must travel, but reality, at the quantum level, exposes a mechanical loophole so absurd it was once dismissed by academia as a mathematical error. In 1962, a physicist named Thomas Hartman was analyzing the mathematical implications of the Schrödinger equation, specifically looking at what happens to a wave function as it passes through a potential energy barrier. Hartman calculated a result that seemed completely nonsensical. His equations showed that once a quantum barrier reaches a certain critical thickness, the time it takes for a particle to tunnel through it stops increasing. It plateaus. If you double the thickness of the barrier, the transit time remains exactly the same. If you multiply the thickness by a factor of 1,000,000, the time it takes for the particle to cross that immense distance does not increase by a single fraction of a nanosecond. For decades, the mainstream academic community dismissed the Hartman effect. It was considered a mathematical artifact, a quirk of the equations that did not represent physical reality. Physicists assumed that while the mathematics might show a constant time, the actual probability of a particle successfully tunneling through such a massive barrier would drop to absolute zero, effectively making the transit time irrelevant. But the experiments of 2025 forced a radical re-evaluation. Utilizing supercooled optical lattices, researchers constructed artificially dense energy fields, scaling the barrier thickness incrementally. They confirmed that while the probability of a successful transit dropped dramatically, requiring immense ensembles of particles to detect a single success, the transit time for the particles that did make it through remained perfectly locked. The constant was maintained. The mathematical implications of this locked transit time are devastating to the classical limits of the universe. Velocity is calculated by dividing distance by time. If the transit time remains a fixed constant near zero, while the distance of the barrier increases exponentially, the effective velocity of the tunneling particle also increases exponentially. It approaches infinity. The particle crosses the expanded barrier definitively faster than a photon traveling through a vacuum. We are no longer discussing a fractional violation of the speed of light. we are observing infinite effective velocity. This immediately triggers the causality crisis. If an object is traveling at an infinite effective velocity, it is entirely bypassing the chronological sequence of the universe. From the perspective of an external observer, in a different reference frame, a particle utilizing the Hartman effect to cross a macroscopic distance would theoretically arrive at its destination before the transmission was even initiated. You would detect the arrival before you witnessed the departure. This is not a theoretical paradox. It is a physical reality that forces us to question if the arrow of time is a fundamental law or simply a local phenomenon experienced only by macroscopic objects trapped outside the quantum domain. We can accept a microscopic particle behaving chaotically, but when an entire complex block of data passes through space without losing a millisecond of latency, that is the moment classical physics begins to collapse. The primary argument against utilizing quantum tunneling for faster-than-light communication has always been the inherent randomness of the quantum state. The wave function dictates probability, not certainty. You cannot predict which specific electron will successfully tunnel and which will reflect. Therefore, sending a structured binary code seemed impossible. If you transmit a signal, it would be randomized into static by the probabilistic nature of the barrier. But modern signal processing and quantum optics have bypassed this limitation not by controlling individual particles, but by utilizing vast ensembles. By encoding the same bit of data across billions of entangled particles simultaneously, researchers ensure that even with a 99% decay rate, the fraction of particles that successfully tunnel retain enough coherent data to reconstruct the original signal on the other side. This statistical reconstruction filters out the quantum noise. In recent laboratory tests, the first superluminal ping was successfully transmitted and verified. A packet of encrypted data crossed a heavily shielded energy barrier without experiencing the latency dictated by the speed of light. The data arrived instantly. This marks the death of latency. The immediate application is a communication network free from the constraints of distance. A transmission from Earth to a receiver on Mars currently takes anywhere from 3 to 22 minutes, depending on orbital positions. Utilizing engineered tunneling barriers, that data could theoretically arrive instantaneously, regardless of the millions of kilometers separating the planets. We are looking at the eradication of communication barriers within our solar system, but telecommunications is merely the proof of concept. If we can reconstruct a stable stream of binary data across an instantaneous probability bridge, the next logical target is physical matter. However, moving from a massless data packet to a physical macroscopic object presents an engineering chasm that requires an entirely new architecture of reality. From transmitting massless data to displacing physical macroscopic matter is a monumental theoretical chasm, but advanced materials science is currently forging an architecture of probabilities designed to bridge that exact void. The primary obstacle preventing a macroscopic object from utilizing the quantum backdoor is the sheer mathematical brutality of probability decay. When a wave function encounters a potential energy barrier, its amplitude drops exponentially with every nanometer of penetration. For a single subatomic particle, this decay is manageable. We can compensate by firing millions of particles to ensure one successfully tunnels. But a macroscopic object is composed of trillions of interacting atoms. To calculate the probability of an entire cohesive object successfully tunneling through a massive physical distance, we must multiply the exponentially small probability of each individual atom. The resulting fraction is so infinitesimally close to zero that it effectively renders macroscopic tunneling impossible under natural conditions. The energy cost required to force a statistically significant probability of transit for a human-sized mass would exceed the total energy output of our Sun. Under the strict laws of natural physics, the barrier remains impassable, but humanity is no longer restricted to naturally occurring physics. We have entered the era of metamaterials. To understand how we intend to bypass probability decay, we must look at materials engineered, not at the chemical level, but at the structural nanoscale. Metamaterials are artificial composite structures designed to exhibit properties that fundamentally do not exist in the natural universe. By precisely arranging nanoscale geometries, we can manipulate how electromagnetic waves, and by extension quantum wave functions, interact with the material. In standard physics, a wave entering a dense medium loses energy and slows down. But metamaterials can be engineered to possess a negative index of refraction, forcing waves to behave in reverse. They can bend light around an object, rendering it completely invisible to specific frequencies. If we can engineer a structure to manipulate the path of a photon, we can theoretically engineer a structure to manipulate the probability amplitude of a quantum state. This is the theoretical foundation of the probability amplifier. Instead of allowing the wave function of a transiting object to decay exponentially as it enters the tunneling barrier, the metamaterial architecture is designed to flatten the energy barrier itself. By creating a highly controlled, localized resonant field, the metamaterial sustains the amplitude of the probability wave, preventing the rapid decay. It creates an artificial tunnel within the quantum tunnel, a protected mathematical corridor where the probability of successful transit remains near 100%, regardless of the physical distance being bypassed. We are not just exploiting a loophole in the physics of reality, we are actively rewriting the code of the barrier. If a metamaterial chassis can stabilize the quantum probability of a macroscopic mass, it sets the stage for instantaneous spatial displacement. But sustaining the probability is only half the equation. The far more terrifying challenge is keeping the object intact. The greatest enemy of macroscopic quantum states is a phenomenon known as quantum decoherence. In the subatomic realm, particles can easily exist in a state of superposition, holding multiple possibilities simultaneously until observed. But the macroscopic universe is inherently hostile to superposition. The moment a quantum system interacts with its external environment, whether through a stray photon, a fluctuation in thermal radiation, or a microscopic gravitational shift, the superposition collapses. The system is forced to choose a definitive state. This is decoherence. It is the mechanism that anchors our macroscopic reality, forcing objects to exist in only one place at a time. If we attempt to tunnel a macroscopic object, it must be converted into a coherent wave function. If even a single particle of external environmental radiation penetrates the metamaterial shielding during the instantaneous transit, the entire system will suffer premature decoherence. The wave function will collapse, not at the destination, but randomly across the vast expanse of the tunneling sequence. The object would be instantly disintegrated, its constituent atoms scattered across millions of kilometers of empty space. Therefore, the metamaterial architecture must act as an absolute coherence field. It must isolate the internal macroscopic structure from the observation of the universe itself, creating a pocket of absolute zero interaction. We must blind the universe to the object's existence before we can mathematically move it. Do not think about building a propulsion system that pushes a spacecraft faster through the void of space. That is a primitive application of classical mechanics. Think instead of a machine that mathematically deletes a physical vessel from its coordinates in our solar system and forces the underlying probability engine of the universe to print that exact vessel into existence at the Alpha Centauri star system. This is the ultimate objective of the macroscopic leap. We are conceptualizing what theoretical physicists refer to as a tunneling drive. To achieve this, the vessel must be encased in a macroscopic coherence field generated by the metamaterial architecture we previously examined. This field acts as an absolute quarantine zone. It ensures that the internal state of the vessel, including every biological entity within it, remains in a localized state of quantum superposition, completely severed from the observational framework of the external universe. The moment this isolation is achieved, the vessel technically ceases to exist in standard classical reality. It becomes a pure probability wave, an incredibly complex mathematical function hovering inside an artificially flattened energy barrier. We must isolate the macroscopic mass from the cosmic background radiation, from stray gravitational waves, from the very fabric of space-time itself. If a single point of data escapes the coherence field, the universe observes the vessel and the wave function violently collapses. The fundamental difference between a tunneling drive and any conventional or theoretical propulsion system, like a warp drive or an antimatter engine, is the complete absence of acceleration. Acceleration requires the application of kinetic force over a duration of time to increase velocity across a physical distance. According to the rigid laws of special relativity, accelerating any mass toward the cosmic speed limit requires an exponentially increasing amount of energy. As you approach the velocity of a photon, the relativistic mass of the object theoretically approaches infinity, and the passage of time experienced by the crew slows to a crawl relative to the rest of the universe. This phenomenon, known as time dilation, ensures that a crew might experience a journey of a few months while centuries pass on their homeworld. A tunneling drive bypasses the tyranny of relativity entirely because there is absolutely zero acceleration. The vessel does not travel through the intervening spatial medium. It does not possess a measurable velocity. The mathematical process is strictly a statistical operation of deletion and reconstitution. The probability function of the entire macroscopic vessel is deliberately collapsed at the source coordinates and instantaneously reconstituted at the destination coordinates. You do not experience the journey because mathematically and physically the journey does not exist. The distance between Earth and a distant exoplanetary system simply becomes an irrelevant variable in the tunneling equation. The mechanics of this reconstitution are governed by manipulating the statistical certainty of the target location by artificially inflating the probability amplitude at the destination coordinates to exactly 100%. The metamaterial engine forces the universe to resolve the superposition in only one possible configuration. The vessel vanishes from the launch pad and simultaneously materializes light years away. But bypassing the fundamental geometric structure of space and time demands a localized energy transaction of incomprehensible scale. The universe fiercely protects its macroscopic stability. Forcing a macroscopic object to tunnel requires sustaining the artificial coherence field and flattening the immense potential energy barrier across staggering interstellar distances. The energy required to maintain this probability corridor prevents the wave function from decaying into statistical noise before the reconstitution sequence is successfully triggered. Current theoretical models calculate that the energy cost for a single instantaneous transit of a manned vessel to a neighboring star system would require the total mass-energy conversion of a small celestial body. We are utilizing the mass-energy equivalence principles not to generate physical thrust, but to generate the localized reality manipulation required for the jump. We are talking about an energy output equivalent to annihilating a small moon, entirely converting millions of tons of matter into pure electromagnetic energy simply to power the quantum infrastructure for one singular event. This astronomical energy requirement is the final physical barrier standing between humanity and the stars. It is a monumental hurdle of engineering and power generation rather than a strict prohibition by the laws of physics. The mathematics confirm that the mechanism is valid. We are no longer asking if faster-than-light travel is mathematically permissible within the framework of quantum mechanics. We are now tasked with calculating the exact voltage required to force the universe to execute the command. This transition from theoretical impossibility to immense engineering challenge represents the most significant paradigm shift in the history of human scientific endeavor. The speed of light is not the absolute limit of the universe. It is merely the speed limit of classical observable phenomena. For millennia, humanity has looked up at the night sky and accepted a reality of profound isolation. We assumed that the immense void between star systems was an insurmountable physical barrier, dictating that our species would forever remain anchored to a single, infinitesimal point in the cosmic dark. We believed that to reach the nearest star, we would need to spend generations confined to metal cylinders accelerating through the emptiness, relying on cryogenic suspension, and accepting that any explorers would be permanently severed from the timeline of Earth. But the mastery of quantum tunneling completely redefines our position in the universe. We are no longer bound by the macroscopic illusion of distance. By manipulating the probabilistic infrastructure that underlies physical reality, we are effectively hacking the subatomic source code of the cosmos. The universe is not a rigid geometric structure. It is a highly complex, mathematically fluid construct. When we finalize the engineering of the tunneling drive, we will not travel to the Alpha Centauri system. We will mathematically delete our coordinates in this solar system and force the universe to reconstitute those exact coordinates at the destination. This marks the evolutionary phase transition from a fragile planetary species to a fully integrated galactic civilization. We achieve this not by brute forcing our way through the fabric of space, but by understanding that space itself is a variable that can be entirely eliminated. The speed of light does not protect us from the vastness of distance. It merely traps us in a predictable linear reality. If this fundamental law collapses, the next inevitable casualty of quantum mechanics is time itself. Next part, we will uncover a far more terrifying scientific mystery, examining the severe physical anomalies and causality paradoxes that occur when a macroscopic object arrives at a destination before it ever departs. What happens to a macroscopic body when the mathematical event of its arrival strictly deletes the event of its departure? Physics has an answer, and it is brutally unforgiving. We look up at the night sky and perceive time as an arrow, a relentless forward march dictating the life and death of stars. However, general relativity does not mandate this forward momentum. Space-time is a mathematical manifold, and within its equations lie coordinates where the distinction between past and future disintegrates. We have romanticized the idea of traveling backwards, but we forgot to calculate the biological and thermodynamic cost of existing in reverse. The universe does not just forbid it, it physically weaponizes reality against it. To understand the severity of this cosmic violation, we must first examine the framework of our reality, the light cone. In Minkowski space-time, your current position is the apex of a cone. Everything that can possibly affect you lies in the past light cone. Everything you can possibly affect lies in the future light cone. The boundary between them is the speed of light. To step outside this cone is to sever the chain of causality. You are no longer participating in the chronological progression of the cosmos. But gravity, the bending of the manifold itself, offers a mathematical loophole. When mass reaches extreme densities, it drags space-time along with it. Consider a Kerr black hole, a singularity spinning at a significant fraction of the speed of light. It does not just warp space. It twists time into a vortex. This is frame dragging. At the innermost boundary, just outside the event horizon, the distortion becomes so severe that the temporal dimension curves back onto itself. Mathematical models prove that the path exists. We call it a closed timelike curve. But navigating a closed timelike curve requires facing an immediate, localized apocalypse. The entropy inversion. Let us place a theoretical macroscopic object, a human observer, into this extreme gravitational environment. You cross the threshold. The geometry of space-time mandates that your trajectory now points toward yesterday. I thought entering the temporal anomaly would be the ultimate terror, but the true horror lies in what happens to the human body when the laws of thermodynamics are violently inverted. The second law of thermodynamics is the dictator of biological existence. Entropy must always increase. Energy disperses. Cells degrade. And heat flows from hot to cold. This law is tethered to the forward arrow of time. When you traverse a closed timelike curve, your localized time vector reverses. your entropy must decrease. But the human biological machine is designed as an entropy generator. Therefore, to exist in a reversed time state, your biological processes must operate in strict opposition to their fundamental design. Within the first few milliseconds, the thermodynamic cost becomes apparent. Your lungs must extract carbon dioxide from the surrounding environment to synthesize oxygen. The heat your body radiates is forced back into your epidermis, reversing the natural flow of thermal energy. You are not just moving backward. Your cellular structure is actively fighting a thermodynamic collapse. The Lense-Thirring effect around the supermassive singularity creates an ergosphere, a region where space itself is dragged faster than the speed of light. Inside this zone, staying still is physically impossible. You are swept into the rotation, and it is here that the temporal dimension folds. As your trajectory aligns with the curve, the chronological protection of the outside universe vanishes. The neural pathways in your brain rely on sequential chemical reactions. Synapses fire, neurotransmitters cross the gap, and a memory is formed. In a state of entropy inversion, this sequence is mathematically prohibited from occurring in that order. Information is processed before the stimulus is received. The electrochemical gradients across your cellular membranes undergo forced depolarization. We trust the law of cause and effect. But general relativity holds a mathematical loophole that allows the effect to destroy its own cause. As you endure the physiological devastation of the entropy inversion, a far more significant problem is manifesting in the broader geometry of space. Surviving the thermodynamic nightmare is only the physical toll. The true cosmic violation happens when the entity successfully emerges at its destination, yesterday. When you complete the transit through the closed timelike curve, you return to a coordinate in space-time that you already occupy. This is the causality escalation. Let us observe the arrival. You are now occupying a universe that contains two versions of your mass, created from nothing. The universe cannot sustain this mathematical contradiction. The law of conservation of mass and energy dictates that the total energy of an isolated system must remain constant. By injecting your mass into a past timeline, you have spontaneously increased the total mass of the local universe without a corresponding energy source. The universe cannot sustain this mathematical contradiction. And Stephen Hawking figured out exactly how reality executes its quarantine. We must abandon the pedestrian notion of the grandfather paradox. You do not need to deliberately alter a historical event to break the universe. Your mere existence as a duplicated mass in a prior space-time coordinate is a fatal violation of thermodynamic equilibrium. Two identical configurations of macroscopic matter now occupy the exact same timeline. To resolve this, the geometry of the cosmos does not simply push you out, it initiates a localized annihilation protocol. This brings us to the chronology protection conjecture, proposed by Hawking in 1992. He postulated that the laws of physics forcefully prevent macroscopic time travel to protect the chronological integrity of the universe. But how does this protection manifest physically? It relies on the absolute chaos of the quantum vacuum. Empty space is never truly empty. It is continuously boiling with virtual particles, fluctuating in and out of existence, borrowing infinitesimal amounts of energy from the vacuum and returning it instantly. In standard flat spacetime, these quantum fluctuations are merely background noise. But within the warped geometry of a closed timelike curve, the topological structure is looped. When a virtual particle travels through this curvature, it returns to its exact starting point at the precise moment it was originally emitted. The particle then stacks upon its past self in perfect phase alignment. It loops again and again, infinitely. The vacuum polarization amplifies with every cycle. The energy density of the fluctuation skyrockets exponentially. In a fraction of a microsecond, the energy within the temporal loop reaches mathematical infinity. This is not a metaphor. It is a rigorously calculated outcome known as a blue sheet singularity. A wall of infinite radiation forms across the threshold of the temporal distortion. Before your macroscopic body can successfully complete the transit and violate causality, you are struck by a concentrated blast of amplified quantum vacuum energy. The atomic bonds of your biological structure do not just break, they are instantaneously converted into pure radiation. The universe uses the infinite energy of its own quantum baseline to incinerate any macroscopic entity attempting to arrive before it departed. There is no timeline branching. There is no unraveling of reality. There is only the brutal efficiency of standard physical laws correcting a severe geometric error. The speed of light is not merely a speed limit for local traffic. It is the fundamental quarantine protocol of the cosmos. It ensures that cause strictly precedes effect, shielding the fragile thermodynamic progression of the universe from the paradox of infinite regression. Time is not a parameter meant to be traversed backwards by biological entities. Causality is the ultimate immune system of physical reality, and it will mercilessly destroy anything that attempts to bypass its authority. In the next section, we will explore another equally fascinating topic. Scientists just observed a galaxy existing in two places at the same time. The James Webb Space Telescope recently transmitted a dataset that fundamentally disrupts our understanding of three-dimensional space. When researchers analyzed a specific deep field sector, they found a single galaxy occupying two completely different coordinates at the exact same moment. This is not a sensor error or a calibration mistake. It is a literal fracture in our perception of reality. I initially assumed this event was just another standard optical illusion caused by gravitational lensing. But the actual physics behind this specific anomaly dismantles the classical rules of spatial location, pushing us directly toward the theoretical mechanics of faster-than-light travel. The anomaly began as a quiet transmission of raw data from the deep field scan arriving at observation stations on Earth. Astronomers were looking into the ancient void, expecting the usual distribution of distant stellar formations. Instead, the stillness of the deep field was broken by the appearance of two distinct, identical points of light. They were positioned in opposite patches of the surveyed region. Initially, the scientific community assumed these were two separate galaxies that simply shared similar morphological characteristics. Astronomers immediately began rigorous spectroscopic analysis to verify their composition, expecting to categorize them as twin galaxies born in the same local cluster. However, the resulting data presented a mathematical impossibility under standard observation parameters. The chemical signatures, the heavy metal content, and the specific light frequencies matched with absolute precision. Every single metric was identical. The data confirmed an undeniable truth. These are not twins. We are looking at a singular cosmic entity manifesting twice in our current timeline. The object is identical down to the quantum signatures of its stellar nurseries. What makes this specific observation completely different from any previously recorded instance of gravitational lensing is the extreme physical separation between the two images. In standard lensing events, multiple images of a background object appear clustered close together around the massive object bending the light. In this case, the separation is unprecedented, spanning an enormous distance across the sky. The galaxy appears to completely surround our vantage point, creating a vast duplication that defies conventional optical geometry. This massive physical split forces us to reevaluate how light interacts with extreme gravity over billions of light-years. This duplication alone is enough to keep cosmologists awake at night, but when they measured the exact trajectory of the incoming light, they discovered a space-bending mechanism that is far more spectacular. To comprehend the sheer scale of this phenomenon, we must direct our attention to the massive foreground galaxy cluster, positioned directly between Earth and the distant target. This cluster contains thousands of galaxies and an immense concentration of invisible matter. The sheer mass of this foreground structure exerts a gravitational pull so powerful that it physically crushes the fabric of spacetime. It acts as an immense natural magnifying glass, altering the fundamental geometry of the space around it. When the light from the singular background galaxy approaches this region, it encounters a severely warped environment. The light can no longer travel in a straight line toward our solar system. Instead, the photons are forced to diverge. They are compelled to flow around the deep gravitational wells created by the cluster, taking two entirely different, massively curved paths through the cosmos before finally converging at our detectors. Because these two paths traverse different regions of warped space, they cover different physical distances. This creates a profound temporal paradox known as a time delay. Since the speed of light is constant, the light taking the longer, more curved path takes significantly more time to reach us. We are not just seeing the galaxy in two places at once, we are seeing the exact same galaxy at two completely different stages of its evolution simultaneously. One image shows the galaxy as it was millions of years before the other. We are looking at a younger version and an older version of a singular structure, existing side by side in the same astronomical photograph. The mapping of these curved light paths has also exposed the hidden architecture of the universe. Most of the gravitational force bending these light rays does not come from the visible stars and galaxies in the foreground cluster. It comes from a massive, invisible web. The precise angles of the duplicated images allow astronomers to calculate the exact shape and density of the dark matter wells manipulating the region. By tracing the light backward from the two mirrored images, scientists are effectively rendering the invisible visible. The divided light acts as a tracer dye injected into the cosmic ecosystem, highlighting the colossal structures of dark matter that dictate the movement of everything in the universe. We have seen light bend before, but this specific curvature creates a cognitive trap, a parallax effect that forces us to entirely discard our classical definition of location and position. The implications of this observation completely dismantle the foundational principles of classical Newtonian physics. According to standard models of a three-dimensional universe, an object of mass can only occupy one specific set of coordinates at any given chronological moment. The James Webb Space Telescope data shatters this rule on a macroscopic scale. We are no longer dealing with theoretical quantum particles existing in superposition. We are looking at an entire galaxy, containing billions of stars, completely defying the classical laws of location. The object is undeniably there, but our observation creates a permanent optical fracture. This optical fracture creates what astrophysicists refer to as a parallax trap. The dual presence of the galaxy is not a result of the object physically splitting into two distinct bodies. Rather, it is a permanent tear in the optical structure of the universe relative to Earth's perspective. Our vantage point is caught in the crossfire of converging light paths, trapping us in an inescapable celestial double vision. As long as the foreground cluster remains in its current position, and as long as Earth remains in its orbit, this specific galaxy will forever hold two conflicting positions in our night sky. When space-time stretches to this extreme degree, the standard definitions of here and there completely lose their meaning. We are forced to compare this macroscopic phenomenon to the uncertainty principle at the quantum level. Just as an electron's precise location cannot be determined until it is observed, the exact position of this background galaxy becomes indeterminate when viewed through the gravitational lens. The distortion is so severe that spatial coordinates are no longer absolute truths. They are merely localized suggestions, entirely dependent on the path the light took to reach the observer. Rather than viewing this paradox as an observational obstacle, scientists are actively weaponizing this cosmic anomaly to measure the universe itself. The time delay between the two mirrored images transforms the duplicated galaxy into a split lighthouse. By meticulously calculating the temporal discrepancy between the two paths of light, researchers can measure the exact distance the light traveled. These precise measurements are currently being used to recalculate one of the most heavily debated numbers in modern physics, the Hubble constant. The numbers derived from this dual lighthouse are not just solving a cosmological math problem, they are revealing a hidden network that dictates the expansion of the void. For decades, different methods of measuring the expansion rate of the universe have yielded wildly conflicting results. This discrepancy threatens to break our current models of cosmology. However, the data extracted from these warped galaxies provides a highly precise, independent method of calculating this expansion. The early calculations derived from the dual images suggest that the universe may be expanding at a rate that contradicts previous microwave background models. The split light is providing raw, uncorrupted data about how fast space itself is stretching apart across vast cosmic distances. Furthermore, the two distinct images act as anchor points, allowing us to map the invisible dark matter bridge connecting them. Because dark matter interacts only through gravity, it remains completely undetectable to conventional instruments. But by analyzing exactly how the light bends to form these two specific images, cosmologists can reverse engineer the mass required to create such a distortion. The dual galaxy acts as a tracer, outlining the exact density and distribution of the dark matter halo. We are mapping an invisible continent by observing how the ocean currents flow around it. Ultimately, the divided light from this singular galaxy is helping humanity measure the overall curvature of the entire cosmos. Is the universe perfectly flat, spherically closed, or curved like a saddle? By finding more of these specific, extreme lensing events, we can compile enough geometrical data to finally answer this question. The way light bends around these massive structures provides the ultimate test for the geometry of spacetime on the largest possible scales. Looking ahead, upcoming astronomical missions scheduled throughout 2026 are specifically designed to hunt for more of these multi-locational anomalies across the sky. We are launching wide-field surveys dedicated entirely to finding extreme lensing events. This marks a significant philosophical shift in astronomy. We are moving away from viewing the universe as a static, linear grid. Instead, we are beginning to map a fluid, dynamic reality that functions more like an infinite hall of mirrors. But if space can be bent to the point where an object exists in two places at once, can we actively harness this mechanism to bypass the ultimate speed limit of the universe? The transition from observing a macroscopic anomaly to engineering practical interstellar travel requires us to bridge the gap between cosmology and quantum mechanics. At the subatomic level, particles routinely bypass impenetrable energy barriers through a process known as quantum tunneling. A localized electron can essentially disappear from one side of a barrier and instantly materialize on the other without traversing the space in between. For decades, this was strictly a microscopic phenomenon. However, the duplicated galaxy captured by the James Webb Space Telescope demonstrates that the fundamental rules governing position and location are completely flexible on a universal scale. If the immense gravity of a dark matter cluster can stretch the fabric of reality so severely that an entire stellar system occupies two conflicting coordinates simultaneously, the theoretical foundation for macroscopic spatial manipulation is already established. Nature is showing us that absolute location is an illusion. This revelation provides the missing mechanical link for faster-than-light travel. The objective of theoretical warp physics is not to build a propulsion system that pushes a vessel through space faster than the universal speed limit. The sheer energy required to accelerate mass to the speed of light makes traditional acceleration impossible. Instead, the goal is to redefine the distance itself. By artificially recreating the exact spacetime curvature we are currently observing around these massive gravitational lenses, a highly advanced civilization could fold the space in front of them. we would not be breaking the speed of light. We would be utilizing the same principles of localized tunneling and gravitational warping to create a shortcut through the fabric of the cosmos. The dual image of this distant galaxy is not just an astronomical curiosity. It is nature's own architectural blueprint for a functional warp drive. We must completely discard the outdated concept of a static, linear universe. We are not navigating a rigid three-dimensional grid. We are floating in a fluid, highly dynamic expanse where gravity constantly rewrites the physical distance between stars. Reality on a cosmological scale functions more like an infinite configuration of space-time mirrors. Objects are constantly shifting, duplicating, and projecting localized echoes of themselves across the void. Every time we look into the deep field, we are not seeing the universe as it is. We are seeing a highly distorted optical projection manipulated by invisible wells of mass. Consider the ultimate implication of this discovery. If a distant galaxy can be fractured and duplicated by a foreground lens, there is an absolute certainty that the light from our own Milky Way is undergoing the exact same process. Right now, somewhere in the extreme depths of the cosmos, the light from our solar system is hitting a massive gravitational anomaly and splitting into multiple paths. To an unknown civilization observing the sky, our galaxy is appearing in two completely different locations simultaneously. And because of the time delay, they might be looking at a primitive Earth alongside a future version of our solar system. In this grand architecture, our very existence might simply be a duplicated reflection projected across the dark matter web. In a universe where your location is nothing more than an optical variable, nothing is exactly where it appears to be. Next, we'll address a rather interesting question. Why do quantum field fluctuations mean the universe never truly sleeps? To properly investigate the structural properties of the universe, we must begin by examining the absence of it. We must define what constitutes a true vacuum. In classical physics, a vacuum is defined simply as a volume of space entirely devoid of matter. For centuries, the scientific consensus held that if you were to remove every physical atom from a defined space, you would be left with a state of absolute nothingness, a region possessing exactly zero energy. However, the advancement of quantum mechanics in the 20th century proved this classical assumption to be mathematically and physically incorrect. To understand why true emptiness cannot exist, we must construct a theoretical model of an absolute vacuum and observe what remains when all known physical phenomena are systematically eliminated. Imagine a sealed container positioned in the deepest regions of intergalactic space, located millions of light-years from the nearest galaxy or star system. This placement minimizes the initial presence of baryonic matter and gravitational influence. The first step in creating our perfect vacuum involves the complete extraction of all particulate matter. We evacuate every hydrogen atom, every rogue electron, and every proton from the interior. The density of physical matter within the geometric boundaries of the container drops to exactly zero. However, removing physical matter is insufficient. The universe is completely permeated by electromagnetic radiation. To isolate the interior, the container must be surrounded by perfect shielding, engineered to block all external wavelengths. We must deflect the cosmic microwave background radiation, the thermal remnant of the Big Bang that uniformly fills all known space. We must block high-energy gamma rays, X-rays, and ultraviolet radiation emitted by distant quasars and active galactic nuclei. Furthermore, we must account for neutrinos. These subatomic particles possess minimal mass and neutral charge, allowing them to pass through standard matter with almost zero interaction. Our theoretical shielding must be dense enough to halt the trillions of neutrinos streaming from stellar fusion reactions across the cosmos. Once the container is isolated from both matter and external radiation, we must address internal thermodynamics. Temperature is a macroscopic measure of the average kinetic energy of particles within a system. To achieve a baseline state of zero energy, we must cool the interior volume to absolute zero, or 0 Kelvin, which equates to minus 273.15 degrees Celsius. At this theoretical limit, all classical kinetic motion ceases entirely. There is no thermal radiation, no particle vibration, and no structural movement. According to the principles of classical mechanics established by Isaac Newton and James Clerk Maxwell, the interior of this container has now achieved a state of absolute rest. It contains zero matter, zero radiation, zero heat, and zero energy. It is the perfect void. But when we examine this volume of space through the framework of quantum field theory, the classical model collapses. The assumption that the container holds zero energy relies on a macroscopic misunderstanding of how the universe is constructed at the fundamental level. If we scale our observation down to the subatomic level, approaching the Planck length of 1.6 times 10 to the power of minus 35 meters, we observe that space is not an empty, passive container. Modern physics dictates that the universe is composed of underlying, pervasive quantum fields. There is an electron field, an electromagnetic field, and a quark field, among others. These fields exist everywhere simultaneously, even in the complete absence of physical particles. Particles, as we observe them, are merely localized excitations, or localized vibrations, within their respective underlying fields. Therefore, to achieve a state of true emptiness, the energy within all of these overlapping quantum fields would have to drop to exactly zero, remaining perfectly flat and motionless. This brings us to a fundamental limitation encoded into the mechanics of reality, the Heisenberg uncertainty principle. Formulated by Werner Heisenberg, this principle states that it is impossible to simultaneously know both the precise position and the precise momentum of a quantum system. This is not a limitation of our measurement instruments. It is an intrinsic structural property of nature. The mathematical inequality dictates that the uncertainty in a system's energy, multiplied by the uncertainty in its time, must always be greater than or equal to a specific non-zero constant, known as the reduced Planck constant divided by 2. If our isolated container were to achieve a state of exactly zero energy, it would mean that the energy value is precisely known with zero uncertainty. Because the universe operates within finite, measurable increments of time, having an energy uncertainty of exactly zero mathematically violates the Heisenberg uncertainty principle. The equations that govern the universe actively forbid any physical system from resting at an absolute zero energy state. Consequently, the quantum fields permeating our evacuated container cannot remain perfectly flat. They are required by physical law to continuously fluctuate. They must constantly shift and vary in energy levels, maintaining a baseline minimum energy known as zero-point energy. The shift from the classical void to the quantum vacuum required a complete re-evaluation of energy conservation. In classical physics, the law of conservation of energy is absolute. Energy cannot be created or destroyed. However, the time-energy uncertainty relation provides a rigid mathematical allowance for energy to be temporarily borrowed from the vacuum itself. The greater the amount of energy borrowed, the shorter the duration it can exist before it must be returned to the underlying field. This precise mathematical relationship governs the behavior of the subatomic interactions occurring within our perfectly isolated container. These unceasing fluctuations manifest in observable reality. They cause the spontaneous creation and immediate annihilation of virtual particle and antiparticle pairs. When a virtual electron and a virtual positron emerge spontaneously from the electron field, they do not violate the macroscopic conservation of energy because their existence is confined to an infinitesimally small window of time. They interact, fulfill the uncertainty requirement, and annihilate, returning the borrowed energy back to the quantum field before any macroscopic deficit can be registered. Even at absolute zero, with all external interference blocked, the interior of our container is saturated with these momentary energy spikes. Space is continuously active, generating and reabsorbing energy in intervals of less than a trillionth of a second. We have systematically removed everything that can be removed from our container. Yet, the vacuum remains dynamic. This underlying mechanical baseline proves that the concept of a completely empty universe is physically impossible. When we look at a region of space, our instruments average out these microscopic fluctuations, presenting the macroscopic illusion of a smooth, empty void. But the empirical data, derived from high-energy particle collisions and precise astrophysical measurements, confirms that the underlying quantum fields are perpetually active. The foundational structure of reality is built upon a constant, unavoidable fluctuation of quantum fields. This is not a theoretical anomaly. It is the fundamental mechanism that governs the existence of all physical matter. Space can never be entirely emptied, and the energy of the universe can never reach an absolute state of rest. I previously established that an absolute vacuum containing zero energy is physically impossible. But to comprehend why reality enforces this limitation, we must examine the governing mathematical framework of the subatomic realm. The impossibility of absolute stillness is not merely a byproduct of complex energetic interactions. It is a rigid, unavoidable mandate encoded directly into the foundational logic of quantum mechanics. To locate the source of this mandate, we must analyze the Heisenberg uncertainty principle. Formulated in 1927 by the German theoretical physicist Werner Heisenberg, this principle represents a definitive break from the determinism of classical Newtonian mechanics. In the classical framework, it is assumed that all physical properties of a system can be measured and known simultaneously with absolute precision, provided the measurement apparatus is sufficiently advanced. Classical physics dictates that a macroscopic object can possess an exact, defined coordinate in space, and an exact, defined trajectory and velocity at the exact same instant. However, Heisenberg demonstrated that this classical assumption breaks down entirely at the subatomic scale. The uncertainty principle asserts that certain pairs of physical properties cannot be simultaneously measured or known to arbitrarily high precision. The most commonly cited pair of these properties is position and momentum. The mathematical law governing this relationship states that the uncertainty in an object's position, multiplied by the uncertainty in its momentum, must always be greater than or equal to a specific, fixed baseline value known as the reduced Planck constant. It is crucial to correct a widespread scientific misconception regarding this principle. The uncertainty is frequently and incorrectly attributed to the observer effect, which is the idea that the physical act of measuring a quantum system inherently disturbs it. While measurement does affect quantum systems, the Heisenberg uncertainty principle is not fundamentally about the limitations of human technology or the interferences caused by physical measurement tools. It is an intrinsic, structural property of nature itself. It dictates that particles simply do not possess exact positions and exact momenta simultaneously. The universe fundamentally lacks absolute mathematical definition at the quantum level. To understand how this relates to our concept of the vacuum of space, we must look at another pair of properties governed by this exact same principle: energy and time. The energy and time uncertainty relation is the specific mathematical dictate that strictly forbids the existence of an empty, zero-energy void. The logic for this relationship is analogous to the position and momentum inequality. It dictates that the uncertainty in the total energy of a quantum state, multiplied by the uncertainty in the time duration over which that state exists, must also be greater than or equal to the reduced Planck constant. We must apply this specific inequality to the theoretical absolute vacuum we attempted to construct previously. Let us hypothesize a defined, isolated region of space where all matter and external electromagnetic radiation have been systematically eliminated, and the internal temperature has been lowered to absolute zero. In classical thermodynamic terms, the total energy of this specific region of space would be exactly zero. If the energy of this defined vacuum is exactly zero, it means that the value of the energy is precisely known, there is no variance, and no statistical ambiguity. Therefore, the numerical uncertainty in the energy is exactly zero. If we insert a value of exactly zero for the energy uncertainty into the Heisenberg equation, the mathematical logic of the physical universe breaks down completely. For the product of the energy uncertainty and the time uncertainty to remain greater than the required constant, while the energy uncertainty is exactly zero, the required uncertainty in time would have to become infinitely large. In the context of physical reality, an infinite uncertainty in time poses a catastrophic physical paradox. The universe is a dynamic, evolving structure that operates within finite, measurable durations and specific causal sequences. A physical state requiring an infinite time interval to be properly defined cannot exist within a functional, temporal universe. Because an infinite time requirement is physically invalid and impossible to achieve, it follows necessarily that the energy uncertainty can never mathematically equal exactly zero. This rigorous logical proof demonstrates that a physical system, even a completely isolated spatial vacuum devoid of all physical particles, can never settle into an absolute minimum energy state of zero. The energy of the vacuum is required by the fundamental laws of quantum mechanics to maintain a non-zero value and to continuously fluctuate over time. The absolute lowest possible energy state that any quantum mechanical system can possess is therefore not zero, but a positive baseline value known as zero-point energy. To contextualize zero-point energy, physicists frequently utilize the theoretical model of a quantum harmonic oscillator. In classical mechanics, a simple harmonic oscillator, such as a mass attached to a spring, can come to a complete and total stop, resting at the absolute bottom of its potential energy well with precisely zero kinetic energy. However, when physicists apply the equations of quantum mechanics to a simple harmonic oscillator, the mathematical solution for its ground state, which is its lowest possible energy level, yields a value of 1/2 multiplied by the Planck constant multiplied by the angular frequency. This mathematical result is explicitly non-zero. The quantum oscillator is physically compelled to maintain a minimum level of vibrational energy, often referred to in literature as zero-point motion. When quantum field theory treats the fundamental fields of the universe, such as the electromagnetic and nuclear fields, as an infinite collection of these coupled oscillators existing at every single point in space, it becomes evident that every coordinate in space must possess this irreducible zero-point energy. The vacuum is defined simply as the state where all these infinite oscillators are in their lowest possible ground state. But as proven by Heisenberg's equations, that ground state remains highly energetically active. Because these fields cannot rest at a zero state, they exist in a perpetual state of oscillation. These micro-oscillations are the physical manifestation of the uncertainty principle, forcing the energy values to vary constantly over infinitesimally small fractions of a second. The universe is fundamentally barred by its own physics from achieving static equilibrium. When we scale this principle across the entire observable volume of the cosmos, the physical implications are absolute. Every single cubic millimeter of space, from the vast interstellar voids existing between galaxy superclusters to the microscopic subatomic gaps between the electrons and protons within the atoms of your own body, is subjected to this Heisenberg dictate. There is no physical or theoretical sanctuary from quantum uncertainty. The macroscopic universe we observe, with its seemingly stable stars, predictable planetary orbits, and silent deep space expanses, is built directly on top of this foundation of forced subatomic restlessness. The classical, empty void is merely a statistical average, a macroscopic simplification of a microscopic environment that is mandated by mathematical law to be continuously active. The equations that govern the foundational layer of reality do not permit silence. The universe is an active construct, permanently running at a baseline level of operation, legally forbidden by its own physical constants from ever shutting down. In the time it takes you to blink your eyes, trillions upon trillions of microscopic entities have sparked into existence and violently annihilated each other right in front of you. They surround you, they pass through you, and they populate the deepest, darkest voids of the observable universe. We have established that the mathematical framework of the cosmos absolutely forbids a state of zero energy. The Heisenberg uncertainty principle acts as an unbreakable cosmic mandate, forcing the underlying energy of the vacuum to continuously jitter and fluctuate. But how does this abstract mathematical uncertainty translate into the physical, three-dimensional reality that we inhabit? What does a restless, vibrating vacuum actually look like when we magnify the empty space between the atoms? To answer this, we must shift our perspective away from the classical concept of solid particles and embrace the foundational premise of quantum field theory. In our everyday experience, we tend to think of the universe as a vast, empty container populated by isolated, solid objects. We picture atoms as tiny billiard balls bouncing around in a void. However, modern physics reveals that this view is fundamentally flawed. The universe is not a collection of isolated objects. It is a complex, overlapping network of continuous, dynamic fields that stretch across the entire expanse of space and time. Imagine an infinite, invisible ocean. Now, imagine dozens of these oceans existing in the exact same space, perfectly overlapping each other. There is an ocean representing the electron field, an ocean representing the electromagnetic field, an ocean for the up quark, an ocean for the down quark, and so on. Every fundamental particle in the standard model of physics is simply a localized vibration, or a wave, traveling through its respective underlying field. When an electron moves through space, it is not a solid sphere traveling through a void. It is a ripple moving across the surface of the infinite electron field. Now, we must apply the mathematical mandate of the uncertainty principle directly to these overlapping infinite oceans. Because the energy of these fields can never drop to absolute zero, the surface of these oceans can never be perfectly still. They cannot freeze into a smooth, mirror-like surface. Instead, the forced minimum energy requirement causes the fields to boil. They are in a perpetual state of agitation, constantly churning and producing spontaneous, localized ripples. These spontaneous ripples are what physicists call virtual particles. Because the fields are vibrating with zero-point energy, they frequently generate enough concentrated energy at a specific coordinate to momentarily manifest a physical particle out of the apparent nothingness. However, the universe operates under strict conservation laws. A particle cannot simply appear without balancing the cosmic ledger. Therefore, these virtual entities always burst into existence as a mirrored pair. Out of the churning vacuum, a virtual particle and its corresponding antimatter twin will spontaneously materialize. For example, a localized spike in the electron field will simultaneously produce a negatively charged virtual electron and a positively charged virtual positron. For a fleeting fraction of a moment, these two entities possess mass, charge, and physical presence. They have borrowed the energy required for their own existence directly from the restless quantum vacuum, but the physical laws governing the universe dictate a strict parameter for this transaction. The energy required to create these virtual pairs was essentially borrowed from the baseline energy of the void and the uncertainty principle dictates that this energetic discrepancy must be resolved almost instantaneously. The duration for which these virtual particles are allowed to exist is inversely proportional to the amount of energy they temporarily harness. Because they possess actual mass, the energetic requirement is relatively massive, meaning their permitted lifespan is unfathomably short. Before they can travel any meaningful distance, and before they can interact with the macroscopic world in any permanent or lasting way, the virtual electron and the virtual positron are drawn back together by their opposing electromagnetic charges. In a time window shorter than a trillionth of a second, they collide and completely annihilate one another. The mass they temporarily possessed is instantly converted back into raw energy, returning to the underlying quantum field and perfectly settling the systemic energy requirement. The local energy state drops back to its baseline, only for the entire violent process to repeat itself an instant later in another location. This continuous, frantic cycle of spontaneous creation and immediate destruction is happening everywhere, all the time. It is happening in the empty space between the stars. It is happening inside the absolute vacuum chamber we constructed in our initial thought experiment, and it is happening in the microscopic gaps between the electrons and the nucleus of every single atom in your physical body. The void is not an empty stage. It is a boiling, chaotic arena of phantom particles flashing in and out of reality faster than any human instrument could ever hope to directly capture. The legendary theoretical physicist John Archibald Wheeler coined a highly specific scientific term to describe this hyperactive subatomic environment. He named it the quantum foam. To properly conceptualize Wheeler's proposition, imagine flying an airplane high above a massive ocean. From a cruising altitude of 40,000 feet, the ocean appears perfectly smooth, flat, and utterly calm. This represents the macroscopic view of the universe. It is how space looks to our human eyes and to our standard optical telescopes. The void seems serene and completely featureless. But as you descend rapidly toward the surface of the water, the illusion of smoothness begins to break down. You start to observe rolling waves and deep shifting swells. If you drop down directly to the surface level, you find a turbulent, highly chaotic environment consisting of crashing waves, breaking crests, and churning white foam. This represents the true quantum view of reality. When we zoom down beyond the atomic scale to the Planck length, the very geometry of space and time becomes turbulent and violently contorted by the endless overlapping storm of virtual particle annihilation. The reality of the quantum foam fundamentally alters our scientific understanding of the physical cosmos. It means that the fabric of the universe is not a passive or static container. It is an active, aggressive participant in the mechanics of physical existence. The empty space is heavy with raw potential, constantly vibrating with the invisible mechanics of subatomic generation and destruction. We are forced to permanently abandon the comforting notion of a quiet, silent cosmos. Instead, we must accept the empirical fact that we exist within a relentless, microscopic storm that never pauses, never slows down, and fundamentally refuses to rest. Yet, a critical analytical question immediately arises from this conclusion. If these virtual particles exist for such an unimaginably brief period, and if they always annihilate each other before they can permanently interact with the standard matter of our observable world, how do we know they are actually there? How can the scientific community be so absolutely certain that this turbulent quantum foam is a physical reality and not just a theoretical convenience created to balance complex mathematical equations? The answer lies in the fact that while the individual particles themselves are fleeting ghosts, the collective physical pressure they exert on the macroscopic world is very real, measurable, and undeniable. I always assume that because virtual particles exist for less than a trillionth of a second, they could never physically affect the macroscopic world we live in. I thought they were just mathematical anomalies, phantom ripples trapped forever in the subatomic realm, completely disconnected from the solid reality of our everyday lives. But the experimental truth is far more profound. These invisible, fleeting quantum fluctuations generate a collective physical pressure that is strong enough to physically move solid metal. The vacuum of space possesses measurable mechanical strength. To bridge the gap between theoretical mathematics and physical reality, the scientific community faced a monumental challenge. If the quantum foam is composed of particles that materialize and annihilate in fractions of a nanosecond, and if these particles cannot be directly captured or photographed by any conventional detector, how can we prove they actually exist? For a long time, the concept of a boiling vacuum was treated with deep skepticism, viewed by some as an artifact of incomplete equations rather than a physical truth. The definitive proof required a shift in perspective. Instead of trying to catch a single virtual particle, scientists needed to measure the collective environmental impact of the entire infinite ocean. The breakthrough arrived in the year 1948, courtesy of a brilliant Dutch theoretical physicist named Hendrik Casimir. At the time, Casimir was working at the Philips Research Laboratories in the Netherlands. He was not initially attempting to prove the existence of the quantum vacuum. Instead, he was investigating the properties of colloidal solutions and the complex intermolecular attractions known as van der Waals forces. However, his rigorous mathematical analysis of how electromagnetic fields interact with conductive surfaces led him to a startling and entirely unexpected theoretical prediction regarding the nature of empty space. Casimir proposed an experiment that was beautifully simple in its concept, but technologically impossible to execute with the tools available in the 1940s. He asked the scientific community to imagine placing two perfectly flat, highly polished, uncharged, and highly conductive metal plates inside our theoretical absolute vacuum. These plates must be placed incredibly close to one another, positioned precisely parallel, and separated by a microscopic distance measuring only a few nanometers. This gap is thousands of times thinner than a single strand of human hair. In a classical, non-quantum universe, these two uncharged plates would simply sit there, completely motionless. There is no electrical charge to pull them together, and their mass is far too small for their mutual gravitational attraction to cause any observable movement. But Casimir realized that the presence of the conductive metal plates would fundamentally alter the behavior of the quantum fields occupying that specific region of space. To understand why, we must recall that virtual particles, specifically virtual photons of the electromagnetic field, behave as waves in the infinite, unrestricted void of open space outside the plates. The electromagnetic field can fluctuate with any possible wavelength. The quantum foam boils freely, generating virtual photons of all sizes, from the infinitely small to the infinitely large. There are no boundaries, so the mathematical solutions for the field are limitless. However, the microscopic gap between the two metal plates creates a strict physical boundary condition. The conductive surfaces of the plates act as perfect mirrors for these virtual electromagnetic waves. Because the field must drop to zero at the surface of the perfectly conductive boundaries, only virtual particles with wavelengths that fit precisely within the gap can materialize. An exact integer number of half wavelengths must fit perfectly between the two walls. This means that any virtual photon possessing a wavelength larger than the physical distance between the plates is mathematically and physically excluded from existing within that specific volume of space. The gap actively suppresses the formation of larger quantum fluctuations. The infinite ocean of the vacuum has been artificially restricted. This restriction creates a profound and measurable environmental imbalance. In the unrestricted space outside the plates, the quantum fields continue to generate the full, infinite spectrum of virtual particles. But inside the gap, a significant portion of that spectrum is missing. Consequently, there are literally more virtual particles popping into existence and colliding with the outside surfaces of the metal plates than there are materializing and pushing against the inside surfaces. In physics, a difference in particle density translates directly into a difference in pressure. Because there is more quantum activity on the outside, the vacuum pressure exterior to the plates is strictly greater than the vacuum pressure occupying the interior gap. The result is a net inward force. The empty space outside actively pushes the two solid metal plates together. The plates are driven toward each other not by gravity, not by residual static electricity, and not by any external mechanical mechanism. They are moved by the physical weight and relentless pressure of nothingness itself. This phenomenon became known worldwide as the Casimir effect. For decades, Casimir's elegant prediction remained purely theoretical. The force generated by the quantum vacuum is incredibly weak at macroscopic distances, requiring the plates to be positioned with sub-microscopic precision while completely isolating the experiment from thermal noise, seismic vibrations, and trace static charges. It was not until the year 1997, nearly 50 years after the initial prediction, that technology finally caught up to the mathematics. An American physicist named Steve Lamoureux, operating at the University of Washington, successfully conducted a definitive and highly precise measurement of the Casimir force. Because aligning two perfectly flat macroscopic plates at a distance of a few nanometers is nearly impossible without them snagging on microscopic surface irregularities, Lamoureux brilliantly modified the experiment. He utilized a spherical lens coated in gold and a flat plate also coated in gold, connected to an ultra-sensitive torsion pendulum housed inside a highly evacuated chamber. As he slowly moved the gold sphere closer to the flat plate, closing the gap to less than a single micrometer, the torsion pendulum registered a distinct, measurable, attractive force. The data perfectly matched Hendrik Casimir's quantum electrodynamics equations with an accuracy of within 5%. Subsequent experiments conducted in the early 2000s using advanced atomic force microscopes have confirmed the effect with even greater precision. The successful measurement of the Casimir effect stands as a monumental triumph of modern physics. It provides absolute, undeniable empirical proof that the quantum vacuum is not an abstract mathematical concept. The void is a physical, interactive component of reality. The restless energy mandated by the Heisenberg uncertainty principle is not confined to the invisible subatomic realm. It scales up. It exerts pressure. It does physical work. We have reached out into the absolute darkest, emptiest nothingness of space, and we have felt it pushing back. I used to believe that the laws of physics were absolute and unforgiving, especially the sacred law of energy conservation. But if you look closely at the mechanics of the void, you discover that the universe operates on an immense, instantaneous credit system, and the quantum vacuum is the ultimate bank. We have seen how the Casimir effect proves that empty space exerts a physical pressure, driven by the ceaseless materialization and annihilation of virtual particles. But this constant generation of mass and energy out of absolutely nothing seems to directly violate the most fundamental rule taught in basic physics classes. The law of conservation of energy explicitly states that energy can neither be created nor destroyed. It can only be transformed from one state to another. How then can the universe legally permit these virtual particles to spontaneously borrow energy from an empty void and burst into physical existence? To understand this cosmic sleight of hand, we must return to the mathematical loophole provided by the Heisenberg uncertainty principle, specifically the relationship between energy and time. In classical thermodynamics, the energy ledger of a closed system must always perfectly balance at every single moment. If you start with zero energy, you must end with zero energy. But quantum mechanics introduces a strict temporal flexibility to this accounting system. The mathematical relation dictates that the uncertainty in a system's energy, multiplied by the uncertainty in the time duration of that state, must be greater than or equal to the reduced Planck constant. Translated into the physical reality of the quantum vacuum, this equation means that the universe allows for temporary, localized violations of energy conservation. A specific coordinate in empty space is entirely permitted to spontaneously spike in energy, effectively creating matter from nothing under one strict and absolute condition. The borrowed energy must be repaid to the vacuum before the macroscopic laws of physics can register the deficit. The universe acts as a highly regulated financial institution. It is willing to grant instantaneous, high-interest loans of raw energy to the underlying quantum fields, but the duration of the loan is directly and inversely tied to the size of the debt. If a quantum field needs to borrow a massive amount of energy to spontaneously generate a heavy, complex virtual particle, the universe grants the request, but demands that the debt be settled in an unimaginably tiny fraction of a second. The heavier the particle, the shorter its permitted lifespan. Conversely, if the field only borrows a very small amount of energy to create a highly energetic but nearly massless virtual photon, it is allowed to hold onto that loan for a marginally longer period. However, regardless of the size of the transaction, the cosmic ledger must eventually be balanced. The virtual particles are violently pulled back together and annihilated, returning the exact amount of borrowed energy back to the baseline field. This continuous loop of borrowing and repayment is the foundational mechanism of quantum electrodynamics, the most accurate and heavily tested theory in the history of human science. Quantum electrodynamics describes how light and matter interact at the most fundamental level. In the classical view, a vacuum is treated as a bankrupt vault containing zero capital. It is a dead, inactive space where nothing happens unless external energy is forcefully injected into it. But through the lens of modern physics, we realize that the vacuum is actually an infinitely wealthy institution. It operates on an unending, hyperactive cycle of credit and liquidity, constantly shifting vast amounts of energy back and forth across the subatomic threshold. In the 1940s, theoretical physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed the mathematical framework to properly calculate and predict these incredibly complex energy transactions. Feynman introduced a brilliant method for conceptualizing these subatomic events. When we look at the mathematical descriptions of a single electron moving through empty space, we do not see a clean, simple trajectory. Instead, the mathematics reveal a chaotic journey through the quantum foam. The electron is constantly emitting and reabsorbing virtual photons. It is constantly dividing into virtual electron and positron pairs that loop out into the void and immediately snap back together. This is the vacuum debt in physical action. The electron is continuously borrowing energy from the surrounding empty space to interact with itself. This process, known mathematically as renormalization, was initially viewed as an annoying mathematical error in the early equations. The calculations kept producing infinite amounts of energy, which made absolutely no physical sense to the researchers at the time. It took decades of rigorous mathematical refinement to understand that these infinities were actually describing the limitless potential of the vacuum's credit system. The physicists had to figure out how to legally subtract the infinite baseline energy of the void just to calculate the finite, observable properties of the single electron. This historical mathematical struggle perfectly highlights the sheer, overwhelming power hidden within the empty space. We are not dealing with small, insignificant amounts of background energy. The quantum vacuum possesses an infinite capacity for energy exchange, constrained only by the strict temporal limits of the uncertainty principle. Every single point in the cosmos, from the deepest intergalactic voids to the empty space occupying your own living room, is a bustling financial market of energy. It is pulsing with trillions of microtransactions every single millisecond. These transactions are not just background noise. They are the essential processes that keep the structural fabric of reality from collapsing into static non-existence. If the universe were to somehow freeze this credit system, if it were to demand that all energy accounts remain permanently balanced at zero with no allowed fluctuations, the fundamental fields would instantly lock up. The continuous, dynamic exchange of energy is what gives space its physical properties. We must therefore completely reframe our understanding of nothingness. The void is not defined by the absence of energy, but rather by the perfect, instantaneous balancing of infinite energetic debts. The virtual particles that populate the quantum foam are the physical currency of this system. They are born out of a mathematical necessity to keep the energy uncertainty greater than the required constant. They live their incredibly brief lives solely to fulfill the terms of their cosmic loan, and their inevitable annihilation is the repayment that maintains the stability of our macroscopic universe. This realization changes how we view the physical matter that makes up our observable world. We tend to separate solid matter from empty space. We think of the atoms in our bodies as permanent, independent structures standing in contrast to the dynamic, fleeting nature of the quantum vacuum, but the truth is much more integrated. The physical matter that constructs the stars, the planets, and biological life is deeply and permanently entangled with this continuous energy exchange. Without the ceaseless borrowing and the restless noise of the quantum foam, the solid matter of our universe would immediately destabilize. The void is not just an empty stage for matter. It is the active, vibrating foundation that anchors our reality. When we consider the vastness of the cosmos, it is very easy to fall into the conceptual trap of separating the cold, empty voids of deep space from the warm, solid matter that makes up our everyday physical world. We tend to view the vacuum as a distant environment, a massive ocean that exists only outside the boundaries of our planet's atmosphere. However, the relentless activity of the quantum foam does not stop at the edge of solid matter. The exact same boiling void that stretches across the billions of light-years between galaxy clusters also permeates the microscopic internal structures of everything you can see and touch. In fact, modern physics reveals that this restless quantum vacuum is the fundamental anchor that holds your physical body together. To truly understand our profound physical connection to the vacuum, we must zoom in past the cellular level, past the complex molecular structures of human biological life, and look directly at the anatomy of a single, fundamental atom. In traditional textbook illustrations, an atom is depicted as a miniature solar system. There is a dense, central nucleus composed of protons and neutrons, surrounded by a vast expanse of empty space, with tiny electrons orbiting the center like planets around a star. But just like the macroscopic illusion of the silent cosmos, this clean, classical diagram is a massive simplification of a highly chaotic and violent reality. The space inside an atom is not empty. The distance between the orbiting electron and the central nucleus is flooded with the exact same fluctuating quantum fields that populate deep space. The electron is not traveling through a sterile, passive void. It is forcing its way through a dense, highly active storm of virtual particles. And because the electron is a fundamental particle possessing a negative electric charge, it actively interacts with this storm in a way that fundamentally alters the structure of physical matter. According to the established principles of quantum electrodynamics, the presence of a raw, charged particle, like an electron, acts as a massive disruption to the surrounding vacuum. As the electron moves through space, its negative charge polarizes the quantum foam around it. When virtual pairs of electrons and positrons spontaneously burst into existence near the real electron, they do not just annihilate randomly. The strong electromagnetic field of the real electron reaches out and manipulates them during their incredibly brief fraction of a second of life. Because opposite charges attract, the positively charged virtual positrons are pulled slightly closer toward the real electron, while the negatively charged virtual electrons are pushed slightly further away. This immediate microscopic realignment of virtual particles creates a localized phenomenon known as vacuum polarization. The real electron effectively wraps itself in a tightly bound, shifting shield of positively charged virtual positrons. This dynamic, vibrating shield acts as a physical screen that dampens and obscures the true, raw electrical charge of the central electron from the rest of the universe. When physicists measure the charge of an electron in a laboratory setting, they are not actually measuring the bare, fundamental charge of the particle itself. They are measuring the reduced effective charge that manages to leak through this thick, buzzing cloud of virtual quantum entities. The vacuum acts as a subatomic filter, softening the extreme electrical forces that dictate how particles interact with one another. The implications of vacuum polarization for the stability of matter are absolute. The precise structural properties of every element in the periodic table depend entirely on the specific, delicate balance of electromagnetic interactions between electrons and their atomic nuclei. If the quantum vacuum were to suddenly fall silent, if it were to stop producing the virtual particles that form these protective shields, the effective charge of every single electron in the universe would instantly spike to its true, unfiltered level. The sudden, massive increase in electromagnetic force would completely destabilize the orbital mechanics of every atom in existence. The intricate bonds that hold complex molecules together would shatter under the immense strain. Chemistry, biology, and all structured physical matter would immediately break down and disintegrate into a chaotic, formless soup of subatomic radiation. The stability of your DNA, the structural integrity of the Earth beneath your feet, and the nuclear fusion powering the Sun all rely heavily on the constant, mediating presence of the restless void. This interaction between solid matter and the fluctuating vacuum is not merely a theoretical assumption, it is an empirically proven physical fact, famously verified in 1947 by the American physicists Willis Lamb and Robert Rutherford. They were conducting highly precise microwave experiments to measure the exact energy levels of an electron orbiting the nucleus of a hydrogen atom. According to the strict classical equations of quantum mechanics at the time, two specific orbital states of the hydrogen electron were predicted to possess the exact same energy level. However, when Lamb conducted his measurements, he discovered a tiny, distinct discrepancy. The energy levels were not exactly equal. One state possessed a slightly higher energy than the other. This minute difference, which became known worldwide as the Lamb shift, sent a shockwave through the global scientific community. It could not be explained by any existing classical or early quantum theory. The puzzle was ultimately solved by incorporating the dynamic interactions of the quantum vacuum. The electron in the hydrogen atom is not orbiting through an empty space. It is constantly interacting with the virtual particles of the surrounding quantum foam. As it pushes through this boiling subatomic ocean, it experiences a very real, measurable resistance, causing its orbit to jitter and subtly shifting its baseline energy level. The Lamb shift provided the first undeniable, direct experimental evidence that the structure of an atom is physically shaped by the fluctuations of the surrounding void. We are forced to recognize a profound shift in our physical reality. You are not a separate, isolated entity, merely passing through the empty space of the universe. Your physical existence is permanently, actively entangled with the ceaseless energy of the void. The atoms that construct your biological form are continuously maintained and stabilized by trillions of microscopic interactions with phantom particles that live and die in a fraction of a second. The vacuum is not just the stage upon which the drama of matter unfolds, it is the physical anchor that prevents the entire production from collapsing into absolute oblivion. This continuous subatomic relationship challenges our deepest philosophical concepts regarding the boundary between something and nothing. When you touch a solid object, such as a wooden desk or a metal surface, the sensation of resistance you feel is entirely electromagnetic. The electrons in your hand are repelling the electrons in the object. But given what we now know about vacuum polarization, we must understand that this interaction is heavily mediated by the quantum void. The physical touch is a complex negotiation of forces transmitted through a thick, invisible layer of virtual particles constantly erupting from the underlying fields. The line separating physical substance from empty space is entirely blurred. Matter is merely an intense, localized concentration of energy, while the vacuum is a baseline, distributed field of energy that actively interacts with that matter. They are two distinct states of the exact same fundamental reality, bound together by the unyielding rules of the Heisenberg dictate. The stability of the solid universe is a direct consequence of the universe's inability to sleep. The constant, restless noise of the quantum realm is the ultimate architect and protector of the macroscopic world, ensuring that the physical structures we rely on remain completely intact. I have thought that the massive structures of the universe, the giant galaxies, and the endless webs of stars were carved exclusively by the relentless pull of gravity over billions of years. But the terrifying and awe-inspiring reality is that the largest structures in the cosmos were not originally forged by gravity at all. They were born from microscopic errors at the very beginning of time. To discover the ultimate monument to the sheer power of quantum fluctuations, we must look up at the night sky and mentally journey back to the genesis of reality itself. We must rewind the clock 13.8 billion years to the exact moment of the Big Bang. Today, the observable universe is unimaginably vast. It spans a diameter of over 93 billion light-years, filled with billions of galaxies drifting through an ever-expanding dark void. But this was not always the case. If we reverse the expansion of space, the galaxies rush back together, the endless voids shrink. The temperature of the cosmos rises exponentially. Eventually, everything we can see, touch, and interact with is compressed into a region of space smaller than a single grain of sand. We keep rewinding, compressing the entire mass and energy of the universe into a space smaller than a single atom, and finally, down to the subatomic Planck scale. At this unfathomable level of compression, the macroscopic laws of physics, the classical rules of gravity and thermodynamics that govern our daily lives, completely break down. The universe, in its earliest moments, was not a smooth classical system. Because the entire cosmos was subatomic in size, it was dominated entirely by the volatile, unpredictable rules of quantum mechanics. The entire universe was subjected to the strict mathematical dictates of the Heisenberg uncertainty principle. Try to visualize the infant universe. It is an intensely glowing, hyper-concentrated singularity of infinite heat and light. But crucially, because of the uncertainty principle, this primordial singularity could not be perfectly smooth or perfectly uniform. Just as we proved that the modern vacuum of space cannot rest at an absolute zero energy state, the energy density of the newborn universe could not remain perfectly flat. It was forced to vibrate. It was forced to fluctuate. The underlying quantum fields that would eventually form the fundamental particles of our modern universe were experiencing the exact same frantic, unpredictable energy jitters that we observe in our modern vacuum today. Across the unimaginably tiny volume of the primordial cosmos, random microscopic patches of space spontaneously spiked in energy, while neighboring patches momentarily dipped. These micro-jitters created microscopic variations in density and temperature. Some regions of the infant universe became a fraction of a percent denser and hotter than the surrounding regions. In any ordinary, localized circumstance, these microscopic variations would be completely inconsequential. They would act exactly like the virtual particles we discussed earlier. They would burst into existence, fulfill the mathematical requirement of the uncertainty principle, and then immediately annihilate, neutralizing the energy difference and returning the system to its baseline state. The early universe should have simply boiled and churned at the subatomic scale, constantly creating and erasing its own microscopic imperfections. But the early universe was not a static environment. It was about to undergo a cataclysmic, explosive transformation that would alter the destiny of these fleeting quantum fluctuations forever. The universe was expanding, and in its earliest fraction of a second, it was about to expand at a rate that defies all human comprehension. This rapid expansion was driven by a theoretical field known as the inflaton field, an incredibly powerful repulsive force that pushed space itself outward. This period of hyperexpansion is known by cosmologists as cosmic inflation. We will explore the exact mechanics of this expansion in the next phase of our journey, but for now, we must focus on what this expansion did to the microscopic jitter of the quantum void. Because the expansion occurred so rapidly, faster than the speed of light itself, the primordial quantum fluctuations did not have the time to annihilate and average themselves out. Instead, they were caught in the massive outward surge of space-time. The violent stretching of the universe grabbed these subatomic energy spikes and pulled them apart. It dragged them out of the microscopic quantum realm and forcibly dragged them into the macroscopic world. The fleeting, phantom ripples of the quantum foam were instantly frozen into the physical architecture of the cosmos. A dense fluctuation that originally measured less than a billionth of a trillionth of a meter across was suddenly stretched into a massive region of space spanning millions of miles. This event represents the ultimate magnification of the subatomic world. The universe acted as a limitless cosmic photocopy machine. It took the microscopic text of quantum uncertainty, the tiny scars of the boiling vacuum, and enlarged them to fill the entire sky. These were no longer temporary virtual particles bound by a quick repayment schedule. They had become real, permanent physical density variations locked directly into the expanding canvas of our young cosmos. The transition from the microscopic to the macroscopic is a profound concept to internalize. The fundamental laws that dictate the spontaneous creation of a virtual electron in a laboratory vacuum chamber are the exact same laws that dictated the initial distribution of matter across the entire universe. The cosmos is essentially a massive, expanded fractal of the subatomic world. If the Heisenberg uncertainty principle did not exist, if the universe were somehow allowed to possess a perfectly smooth, zero-energy state at the moment of the Big Bang, the entire structure of our reality would be radically different. A smooth, classical Big Bang would have resulted in an expanding universe where matter was distributed perfectly evenly. Every cubic light-year of space would contain the exact same amount of hydrogen gas. There would be no dense regions to exert stronger gravity. There would be no clumping of matter. In a perfectly smooth universe, gravity would pull equally in all directions, canceling itself out. Gas clouds would never collapse to form stars. Stars would never group together to form galaxies. The universe would be a dark, uniform, featureless fog of cooling gas, devoid of structure, light, and life. The only reason we have massive galaxy superclusters, solar systems, and solid planets is because the universe was forced to jitter at its birth. The microscopic errors, mandated by quantum mechanics, provided the essential seeds of structure. We owe our entire macroscopic existence to the fact that the primordial void was fundamentally incapable of being perfect. We left the infant universe at a critical juncture. It was compressed into an unimaginably small volume, driven by the absolute mandates of quantum mechanics. The fundamental fields were boiling, creating subatomic variations in energy and density. Under normal circumstances, these microscopic jitters would have simply canceled each other out, disappearing back into the quantum foam as quickly as they emerged. However, the universe did not remain a subatomic entity It underwent a transformation so violent and rapid that it defies our everyday understanding of physics. This event is known as cosmic inflation, and it is the exact mechanism that grabbed the invisible quantum world and dragged it into the macroscopic reality we inhabit today. To understand how inflation altered the fundamental architecture of the cosmos, we must look at a specific and incredibly narrow window of time. We are not talking about millions of years or even a single second. Cosmologists theorize that the inflationary epoch began at approximately 10 to the power of minus 36 seconds after the absolute beginning of the Big Bang. It ended just a fraction of an instant later, at around 10 to the power of minus 32 seconds. Within this incomprehensibly brief slice of time, the physical dimensions of the universe exploded outward at an exponential rate. This was not an explosion of matter moving through pre-existing space. It was an explosion of space itself. According to Albert Einstein's general theory of relativity, while no physical object can travel through space faster than the speed of light, there is absolutely no speed limit on the expansion of the spatial fabric itself. During inflation, the metric of space expanded at a velocity exponentially faster than light. The universe ballooned by a factor of at least 10 to the power of 26. To put that into a physical perspective, it is equivalent to taking an object the size of a single proton and stretching it out to the size of our entire solar system in less than a trillionth of a second. What was the driving engine behind this terrifying expansion? Theoretical physicists propose the existence of a scalar field, often referred to as the inflaton field. In the extreme conditions of the early universe, this field became trapped in a specific energy state known as a false vacuum. Unlike our modern vacuum, which possesses a small baseline energy, the false vacuum of the inflaton field contained a massive inherent energy density. Crucially, this specific configuration generated a bizarre physical property known as negative pressure. In the framework of general relativity, negative pressure creates a repulsive gravitational effect. Instead of pulling matter together, it violently pushes space apart. This repulsive gravity drove the exponential runaway expansion. But the most profound consequence of cosmic inflation was its effect on the subatomic quantum fluctuations that were boiling within the primordial fields. As space expanded faster than light, it grabbed these tiny, fleeting energy spikes and physically stretched them. Normally, a virtual particle pair or a localized quantum fluctuation would exist for a microscopic fraction of a second before annihilating and returning its energy to the void. But the inflationary expansion happened so quickly that it outpaced the annihilation process. The space containing the fluctuation was stretched outward so rapidly that the high-energy peak and the low-energy trough of the fluctuation were pulled vast distances apart. In cosmological terms, the physical wavelengths of these quantum jitters were stretched beyond the Hubble radius, which is the boundary of the observable universe at any given time. Once a fluctuation is stretched beyond this limit, it loses its ability to interact with itself. The subatomic jitter is effectively frozen. It can no longer annihilate or average out. It becomes a permanent, macroscopic variation locked directly into the physical geometry of space. Through this violent inflationary process, the microscopic uncertainty mandated by Werner Heisenberg was magnified onto a cosmic scale. The tiny, random variations in the quantum foam were transformed into massive, spanning regions of slightly higher or lower energy density. The universe was acting as a flawless amplifier, taking the microscopic noise of the subatomic realm and broadcasting it across billions of light-years. When the inflaton field finally decayed, settling down from its false vacuum state into a true minimum energy state, the era of exponential expansion abruptly ended. The massive amount of energy that had been locked inside the field was suddenly released into the newly expanded universe. This event, known as reheating, generated a blindingly hot, dense plasma of fundamental particles and radiation. The fundamental forces of nature began to separate into their modern forms, and the universe was now macroscopic, incredibly vast, and filled with the raw materials required to build atoms, stars, and galaxies. It was a chaotic furnace of elementary particles interacting at energy levels far beyond the capabilities of our most advanced modern particle accelerators. However, because of the frozen quantum fluctuations, this raw material was not distributed perfectly evenly. The regions of space where the quantum jitters had spiked before being stretched now contained slightly more matter and radiation than the regions where the jitters had dipped. The density of the universe varied by roughly 1 part in 100,000 from location to location. These slight variations might seem insignificant, but they were the absolute prerequisite for the existence of the universe as we know it. They were the primordial seeds of cosmic structure. Without cosmic inflation to stretch and freeze the boiling vacuum, the universe would have expanded at a much slower classical rate. The quantum jitters would have neutralized, and the resulting cosmos would be a perfectly smooth, uniform, and completely dead expanse of gas. Instead, we inherited a universe heavily scarred by its quantum origins. The rapid expansion guaranteed that the macroscopic world would be forever dictated by the microscopic rules of the void. We have established that these macroscopic scars exist, but up to this point, they have remained a theoretical description based on advanced mathematics. The next logical question is whether we can actually prove that these ancient, stretched-out quantum jitters are real. Can we look out into the deep void and actually observe the physical fingerprints of cosmic inflation? The answer is a definitive yes, and the proof is hiding within the oldest light in existence. We do not have to rely solely on theoretical deduction and complex mathematics to prove that cosmic inflation stretched the subatomic quantum vacuum into macroscopic reality. We actually possess a pristine, highly detailed physical photograph of these ancient quantum fluctuations. It is the oldest light in existence, and it surrounds our planet from every possible direction. To understand how we obtained this monumental image, we must examine the thermodynamic history of the early universe, specifically focusing on an epoch that occurred roughly 380,000 years after the initial expansion of the Big Bang. Prior to this specific era, the universe was entirely opaque to light. The immense heat and density of the post-inflationary cosmos meant that atomic nuclei and electrons could not bind together. They existed as a hyperactive boiling plasma consisting of unbound protons, helium nuclei, and free electrons. This dense plasma was saturated with photons, the fundamental particles of light. However, because the density of the free electrons was so incredibly high, a photon could only travel a microscopic distance before violently colliding with an electron, a process known to physicists as Thomson scattering. The photons were trapped in an endless pinball game, constantly absorbed and re-emitted, unable to travel in a straight line. If you were somehow able to stand in the universe at this time, you would see absolutely nothing but an intensely glowing, blinding white fog. But the universe was continuously expanding, and as the physical volume of space increased, the overall temperature and density of the plasma began to drop. Approximately 380,000 years after the Big Bang, the ambient temperature of the cosmos cooled to a critical threshold of around 3,000 degrees Kelvin. At this precise thermal boundary, a monumental shift in physics occurred. The kinetic energy of the free electrons dropped low enough that the electromagnetic pull of the protons could finally capture them. This process, known in cosmology as recombination, resulted in the formation of the very first neutral hydrogen and helium atoms. As the free electrons were swept up and bound into stable atomic orbits, the blinding fog of the early universe instantly cleared. The vast empty spaces between the newly formed atoms meant that the photons were finally free to travel in straight lines without constant collision. This moment is referred to as photon decoupling. The light from that exact era has been traveling unimpeded through the vacuum of space ever since, acting as a permanent, observable echo of the primordial universe. As the universe continued to expand over the next 13.8 billion years, the fabric of space stretched these ancient photons, pulling their wavelengths out of the visible light spectrum and deep into the microwave band. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered this leftover radiation using a massive horn antenna in New Jersey. They detected a constant, uniform background noise coming from every direction in the sky, regardless of where they pointed their instrument. They had inadvertently discovered the cosmic microwave background, a faint thermal glow that perfectly matches a temperature of roughly 2.7 degrees Kelvin above absolute zero. Initially, the cosmic microwave background appeared to be perfectly smooth and uniform. To the early radio antennas, the temperature of this background radiation was exactly the same in every single direction. But cosmologists knew that a perfectly smooth background would pose a massive theoretical problem. If the early universe was perfectly uniform, with no variations in density, then gravity would have never been able to pull matter together to form stars and galaxies. The universe would have remained a smooth, featureless cloud of hydrogen gas. For our modern, structured universe to exist, there had to be microscopic variations in the early plasma, and those variations had to be imprinted on the cosmic microwave background. To search for these microscopic variations, the scientific community launched a series of incredibly sensitive space observatories, operating far above the interference of Earth's atmosphere. The Cosmic Background Explorer, launched in 1989, provided the first definitive proof. It was followed by the Wilkinson Microwave Anisotropy Probe in 2001 and the Planck satellite in 2009. These satellites possessed instruments capable of measuring temperature differences down to millionths of a degree. When these observatories mapped the entire sky, the illusion of a perfectly smooth universe was finally shattered. They discovered that the cosmic microwave background is actually covered in a delicate, mottled pattern of temperature fluctuations. These variations, known as anisotropies, represent temperature differences of merely 1 part in 100,000. On the high-resolution maps produced by the Planck satellite, these variations are visually represented by tiny regions of blue and red, indicating areas that are fractionally colder or fractionally hotter than the average background temperature. These microscopic temperature differences are the direct, unedited fingerprints of the subatomic quantum fluctuations that occurred during the birth of the universe. To understand the connection, we must look at the physics of gravity and light. The colder spots on the microwave map correspond to regions of the early universe that were slightly denser. Because these regions contained more matter, they exerted a slightly stronger gravitational pull. When the photons decoupled and began their journey across the universe, the light originating from these denser regions had to expend a tiny fraction of its energy just to climb out of the localized gravity well. This loss of energy caused the light to cool slightly, creating the cold spots we detect today. Conversely, the hotter spots represent regions of space that were slightly less dense. The photons originating from these areas did not have to fight against a strong gravitational pull, allowing them to retain more of their energy and register as slightly warmer on our modern detectors. These exact variations in density were created by the boiling quantum foam, stretched and frozen into the macroscopic fabric of space during the violent era of cosmic inflation. When we study the cosmic microwave background, we are not just looking at the afterglow of the Big Bang. We are looking directly at the ancient, frozen ripples of the restless quantum void. The distribution of these hot and cold spots perfectly matches the mathematical predictions of quantum field theory. It is the ultimate proof that the macroscopic architecture of reality is entirely dictated by the microscopic laws of the subatomic realm. Every galaxy cluster, every stellar nursery, and every planetary system is situated precisely where it is because of a random, unpredictable subatomic jitter that occurred when the universe was smaller than a single atom. Quantum mechanics did not just define the rules of the microscopic world. It actively birthed the entire physical structure of the cosmos. Every single star you see in the night sky, every planet orbiting those stars, and every black hole lurking in the dark exists for one incredibly specific reason. They exist simply because the vacuum of the early universe was slightly imperfect. We have seen how the violent expansion of cosmic inflation grabbed the microscopic, boiling quantum foam and stretched it across the cosmos, leaving behind a permanent physical map of density variations. We captured the exact image of this map in the cosmic microwave background radiation. But how did those tiny, fractional differences in the density of ancient hydrogen gas transform into the massive, complex architecture of the modern universe? To understand this magnificent transition, we must introduce the ultimate sculptor of the cosmos, the relentless and patient force of gravity. When the universe cooled enough to form the first neutral atoms, it was essentially a massive, expanding cloud of hydrogen and helium gas. If this cosmic cloud had been perfectly uniform, gravity would have pulled on every atom equally from all directions. The gravitational forces would have perfectly canceled each other out, and the gas would have remained a stagnant, featureless fog forever. But because of the stretched quantum fluctuations, the cloud was not uniform. There were specific regions where the gas was packed slightly closer together, and regions where the gas was slightly more spread out. In the brutal realm of astrophysics, even the smallest advantage in mass translates directly into a physical advantage in gravitational pull. The regions of space that were slightly denser possessed a fractionally stronger gravitational field than the empty void surrounding them. This tiny difference in gravity acted as a massive cosmic magnet. The dense regions began to slowly and inevitably pull the surrounding hydrogen and helium gas toward them. As more gas fell into these dense pockets, their overall mass increased. As their mass increased, their gravitational pull grew even stronger, allowing them to pull in gas from even further away. This created a runaway gravitational feedback loop that operated over hundreds of millions of years. The dense regions grew denser, while the less dense regions were systematically emptied of matter, creating the vast, dark voids that separate the galaxy clusters we observe today. Deep within the hearts of these growing, dense clouds of gas, the physical pressure began to build to unimaginable levels. As the hydrogen gas was violently compressed by its own collective gravity, the temperature at the core of the clouds began to skyrocket. The atoms were squeezed so tightly together that the electrostatic repulsion between their atomic nuclei was forcefully overcome. At a critical threshold of millions of degrees, the hydrogen nuclei slammed into one another and fused, releasing a colossal burst of nuclear energy. This was the exact moment of cosmic dawn. Out of the darkness of the cooling universe, the very first generation of stars violently ignited. These early stars, composed entirely of pristine hydrogen and helium, were massive, burning with a furious intensity and dying in spectacular supernova explosions that seeded the empty universe with heavier chemical elements. The subtle gravitational wells created by the ancient quantum fluctuations had successfully sparked the first physical light of the macroscopic universe. But gravity did not stop with the formation of isolated, lonely stars. The exact same runaway feedback loop continued to operate on increasingly larger and larger scales. The first stars were drawn together by their mutual gravitational attraction to form the first primitive galaxies. Over billions of years, these early galaxies collided and merged, forming massive swirling spirals and giant elliptical galaxies holding hundreds of billions of individual stars. If we zoom out to the grandest possible scale of the observable universe, we do not see a random, chaotic scattering of galaxies. Instead, we see a highly structured, incredibly intricate pattern known as the cosmic web. The cosmic web is the largest known physical structure in existence. It consists of massive, glowing filaments of galaxies that stretch for hundreds of millions of light-years across the dark void. These glowing filaments intersect at colossal structural hubs called galaxy superclusters, which contain thousands of individual galaxies bound together by gravity. Between these glowing filaments lie the great cosmic voids, massive regions of empty space spanning hundreds of millions of light-years across, containing almost no physical matter at all. The specific structure of this macroscopic cosmic web is not random. When astrophysicists run massive computer simulations of the universe, starting with the exact density variations mapped by the cosmic microwave background, the simulated gravity pulls the gas together to form a cosmic web that perfectly matches the one we observe through our advanced space telescopes. The vast galaxy filaments and the deep, empty voids are the direct, scaled-up physical descendants of the tiny, boiling virtual particles that populated the first fraction of a second of time. Furthermore, the formation of this immense structure required the presence of an invisible, highly mysterious component known to science as dark matter. While the visible hydrogen and helium gas was interacting with light and bouncing around in the early universe, dark matter was completely unaffected by electromagnetic radiation. Because it only interacts through gravity, dark matter was able to begin clumping together much earlier than standard matter. The dense regions created by the quantum fluctuations became the ultimate gathering points for massive concentrations of dark matter. These invisible dark matter halos acted as the foundational scaffolding for the entire visible universe. Their immense gravitational pull provided the necessary anchor for the normal gas to fall into, massively accelerating the formation of stars and galaxies. Without the underlying framework of dark matter, the slight density variations caused by the quantum vacuum would not have possessed enough gravitational strength to form the cosmic web within the 13.8 billion-year lifespan of our expanding universe. So, when we look at a deep-field photograph from the James Webb Space Telescope showing thousands of distant galaxies glittering against the pitch-black darkness of deep space, we are essentially looking at a macroscopic photograph of the subatomic world. The majestic spiral arms of galaxies, the violent birth of new stars in glowing nebulae, and the supermassive black holes anchoring the galactic cores, all of these magnificent cosmic phenomena are merely the localized physical consequences of a strict mathematical uncertainty rule. The universe could not rest at an absolute zero-energy state. The underlying quantum fields had to boil. The universe expanded, stretching the boiling foam into massive density waves. Gravity grabbed those waves and methodically built the cosmic web. You are not separated from the bizarre mechanics of the quantum realm. You are currently living inside the physical magnification of it. The carbon and iron atoms in your biological body were forged in the cores of dying stars, and those stars only existed because a tiny patch of the subatomic vacuum jittered slightly harder than its neighbor at the absolute beginning of time. The grand architecture of reality is nothing more than the physical structured echo of a restless, vibrating void that mathematically refused to be empty. The quantum vacuum did not merely construct the ancient universe and then quietly retire into the background of reality. It remains the absolute dominant force shaping the cosmos right now, in this very second. We have established that the microscopic jitters of the void provided the foundational blueprints for the cosmic web, allowing gravity to assemble the massive galaxy clusters we observe today. However, to witness the current, active, macroscopic manifestation of the boiling vacuum, we must examine one of the deepest and most profound mysteries in all of modern science. We must investigate the phenomenon known as dark energy. In the late 1990s, two independent teams of astronomers embarked on a massive observational project. Their goal was to measure the exact rate at which the expansion of the universe was slowing down. At the time, the standard cosmological model operated on a very logical assumption. The Big Bang initiated the expansion of space. but the collective gravitational pull of all the matter in the universe, including all the stars, galaxies, and invisible dark matter, should be acting like a giant cosmic brake. Gravity pulls things together. Therefore, the expansion of the universe should be gradually decelerating over time. To measure this deceleration, the astronomers looked for highly specific stellar explosions known as Type Ia supernovae. These supernovae occur when a white dwarf star accumulates too much mass from a companion star and detonates in a thermonuclear explosion. Because these specific explosions always occur at the exact same critical mass threshold, they always peak at the exact same intrinsic brightness. By measuring how bright these supernovae appear from Earth, astronomers can calculate their precise distance, earning them the title of cosmic standard candles. The researchers identified dozens of these standard candles situated in incredibly distant galaxies, billions of light-years away. By comparing their distances with the redshift of their host galaxies, which measures how fast the galaxies are moving away from us, the teams expected to see a clear deceleration curve. Instead, the data revealed something entirely impossible according to the physics of the time. The distant supernovae were significantly dimmer than they should have been. They were much further away than the deceleration model predicted. The expansion of the universe was not slowing down at all. It was speeding up. The cosmos was accelerating outward, pushing the galaxies apart faster and faster every single day. This discovery, which later earned the Nobel Prize in Physics, completely shattered the existing cosmological models. Something invisible and incredibly powerful is actively pushing the fabric of space-time apart, completely overpowering the combined gravitational pull of all the mass in the universe. This mysterious repulsive force was immediately labeled dark energy. While the term dark energy sounds like a placeholder for human ignorance, the leading and most mathematically sound candidate for this force is something we have already extensively analyzed. Dark energy is widely believed to be the exact macroscopic manifestation of vacuum energy. It is the cosmological constant, a term originally introduced into the equations of general relativity by Albert Einstein, and it perfectly aligns with the principles of quantum field theory. We have already proven through the Heisenberg uncertainty principle that empty space cannot possess exactly zero energy. The quantum fields are forced to continuously fluctuate, creating a baseline zero-point energy across the entire volume of the void. Because this zero-point energy is an intrinsic, fundamental property of space itself, it possesses a constant energy density. A specific volume of empty space will always contain the exact same baseline amount of quantum energy, regardless of how much it expands or contracts. This is where the thermodynamics of the expanding universe create a terrifying runaway effect. As the universe expands, it creates more empty space. Because the energy density of the vacuum is constant, creating more space inherently means creating more total vacuum energy. In the framework of general relativity, a constant energy density distributed throughout a vacuum creates a specific physical effect known as negative pressure. And, as we observed during the brief epoch of cosmic inflation, negative pressure generates a repulsive gravitational force. It does not pull matter together, it pushes space apart. The microscopic, boiling quantum foam, constantly generating and annihilating virtual particles, is literally exerting an outward pressure on the very geometry of the cosmos. For the first 8 billion years of the universe's history, this repulsive force was kept in check. The universe was relatively small, meaning the total volume of empty space was lower and the density of physical matter was much higher. The collective gravitational pull of the dark matter halos and the galaxy clusters was strong enough to overcome the outward push of the vacuum energy, allowing the cosmic web to form and structure to evolve. But as the universe continued to expand, the physical matter became increasingly diluted and spread out across vast distances. As the galaxies drifted further apart, their collective gravitational grip on one another steadily weakened. Meanwhile, the density of the vacuum energy remained perfectly constant. The expanding volume meant there was simply more space, and therefore more total repulsive vacuum energy. Roughly 5 billion years ago, a critical cosmological tipping point was reached. The total repulsive force of the expanding vacuum finally surpassed the fading attractive force of the diluted matter. The expansion of the universe shifted from a state of deceleration into a state of active, unstoppable acceleration. The vacuum had seized absolute control of the cosmos. When modern cosmologists calculate the total mass-energy budget of the universe today, the numbers reveal a stark reality. All the normal baryonic matter, every star, planet, dust, cloud, and biological organism, makes up less than 5% of the universe. Dark matter accounts for roughly 27%. The remaining 68% of the universe is composed entirely of dark energy. We live in a reality that is overwhelmingly dominated by the invisible, restless energy of nothingness. The subatomic jitter that we mathematically isolated in our theoretical vacuum container is not just a microscopic curiosity confined to laboratory experiments. It is the single most powerful physical mechanism in existence. It is currently tearing the macroscopic universe apart at the seams. And as the expansion continues to accelerate, driven by the ceaseless creation of more vibrating space, the galaxies will eventually be pushed apart at velocities exceeding the speed of light, leaving us in a cold, isolated, and permanently restless void. We have established that the restless energy of the quantum vacuum is the driving force behind the accelerated expansion of the cosmos. This phenomenon, which we observe macroscopically as dark energy, perfectly aligns with the fundamental requirement that empty space must possess a baseline level of energy. It seems like a monumental triumph of modern science. We have successfully connected the microscopic jitter of subatomic fields to the macroscopic fate of the entire universe. However, this apparent victory conceals a massive, glaring paradox that threatens to bring the entire temple of modern theoretical physics crashing down. When physicists sit down to mathematically calculate the exact amount of energy contained within the vacuum, they run into a problem so severe that it has been dubbed the worst prediction in the history of human science. This profound crisis is known among cosmologists and quantum field theorists as the vacuum catastrophe. To understand the scale of this catastrophic miscalculation, we must look at how physicists attempt to determine the total energy density of empty space. According to the standard model of particle physics, the vacuum is filled with overlapping quantum fields. There is an electromagnetic field, a field for the Higgs boson, fields for quarks, and fields for electrons. Because of the Heisenberg uncertainty principle, every single one of these fields must maintain a minimum baseline vibration, or zero-point energy. To calculate the total energy of the vacuum, a physicist must mathematically sum up the zero-point energies of all these fluctuating fields across every possible frequency. They must account for the virtual particles popping in and out of existence at every single coordinate in space. However, as they add up the energies of smaller and smaller wavelengths, the total energy value continues to grow. It grows infinitely large. To stop the calculation from producing an infinite result, physicists have to apply a theoretical cutoff point. They assume that the standard model of physics stops functioning at the absolute smallest measurable scale of reality, known as the Planck length. Even when they apply this extreme mathematical cutoff, stopping the calculation at the smallest possible physical distance, the resulting number is completely incomprehensible. The theoretical calculation predicts that the energy density of the quantum vacuum should be an astronomical figure. Now, we must compare this theoretical prediction to the actual physical reality we observe. Astronomers measure the real-world density of dark energy by observing how fast distant galaxies are accelerating away from us. When we compare the observed physical value to the mathematically predicted value, the two numbers do not match. They do not just slightly disagree. They disagree by a factor of 10 to the power of 120. That is, a 1 followed by 120 zeros. This represents a discrepancy so unimaginably large that the human brain cannot properly contextualize it. It is the largest mismatch between mathematical theory and physical observation in the entire recorded history of science. It means our fundamental equations are predicting an amount of vacuum energy that is 120 orders of magnitude larger than what actually exists in the universe. To truly grasp the severity of this mathematical failure, we must consider what the universe would look like if the theoretical calculations were actually correct. If the quantum vacuum possessed the immense amount of energy predicted by quantum field theory, the repulsive gravitational force generated by that energy would be absolute. In the very first fraction of a second after the Big Bang, this hyperconcentrated dark energy would have violently ripped the fabric of space-time apart. The expansion of the universe would have been so incredibly fast and aggressive that gravity would never have had the chance to pull matter together. Not a single gas cloud could have condensed. Not a single star could have ignited. The formation of galaxies, planets, and biological life would have been physically impossible. Every single atom in existence would have been instantly isolated, pushed away from every other atom at speeds far exceeding the speed of light. The universe would be a dark, sterile, and infinitely empty expanse, torn apart by its own internal subatomic pressure before it ever had the chance to evolve. The very fact that you exist, the fact that you are able to look up at a sky filled with billions of shining stars, is absolute physical proof that the quantum calculations regarding vacuum energy are completely and fundamentally wrong. This massive contradiction reveals a critical, glaring blind spot in our collective understanding of reality. It tells us that while quantum mechanics is incredibly accurate at describing the behavior of subatomic particles in a laboratory, and general relativity is incredibly accurate at describing the behavior of gravity and massive galaxies, the two frameworks are fundamentally incompatible when forced together. The vacuum catastrophe occurs exactly at the intersection where the physics of the incredibly small meets the physics of the incredibly large. We are missing a crucial piece of the cosmic puzzle. Somewhere hidden within the mechanics of the void is a mechanism that violently suppresses the energy of the quantum fields, bringing the massive theoretical value down to the tiny, gentle push of the dark energy we observe today. Theoretical physicists have proposed numerous advanced frameworks to solve this mystery, from supersymmetry to string theory, hoping to find a unified theory of quantum gravity, but as of right now, the true nature of the vacuum remains entirely elusive. The universe is whispering a profound secret about its own construction, and we are currently too deaf to understand the language. We know the vacuum is restless. We know it is pushing the galaxies apart, and we know our mathematical understanding of it is broken. Despite our inability to reconcile the equations, the physical reality of our universe remains unyielding. The cosmos refuses to settle into a state of quiet rest. The dark energy, whatever its true source may be, continues to drive the expansion of the cosmos, setting in motion a runaway feedback loop that guarantees the universe will never fall asleep. Despite the profound mathematical contradictions that currently plague quantum field theory, the physical reality of our universe remains unyielding. Space refuses to settle into a state of quiet rest. As dark energy continues to drive the accelerated expansion of the cosmos, it sets in motion a runaway cosmological feedback loop that guarantees the universe will never fall asleep. To understand the ultimate fate of this restless reality, we must project our current observations deep into the distant future. We must examine the mechanics of an accelerating universe and observe what happens when the relentless pulse of the vacuum finally outlasts the glowing matter that currently illuminates the night sky. Let us begin by mapping out the long-term destiny of a universe that expands forever. At our current cosmological epoch, the universe is roughly 13.8 billion years old. It is an era defined by star formation, massive galaxy clusters, and abundant luminous energy. But this era is merely a temporary phase. As the galaxies continue to drift further apart, pushed outward by the continuous creation of new space and new vacuum energy, the overall density of physical matter will inevitably drop towards zero. The gravitational forces that hold local galaxy groups together will eventually be overpowered by the relentless expansion of the void. Over the next 100 billion years, the night sky will radically change. An observer, located in our solar system, assuming the Earth survives the eventual expansion of the Sun, would no longer see the millions of distant galaxies that populate our current deep space photographs. Those galaxies will have been pushed beyond the cosmological event horizon. They will be receding from us at speeds faster than light, meaning their photons will never be able to cross the expanding gulf of space to reach our eyes. The observable universe will shrink down to our local galactic neighborhood, while the rest of the cosmos fades into an impenetrable, expanding darkness. As time marches forward into the trillions of years, the internal engines of the remaining galaxies will begin to fail. The formation of new stars requires massive, dense clouds of hydrogen gas. But as the universe expands, this raw material becomes increasingly scarce and spread out. Eventually, the gas clouds will be exhausted. The current generation of stars will burn through their nuclear fuel. The massive, brilliant blue stars will detonate in spectacular supernovae, leaving behind black holes and neutron stars. The smaller, longer-lived red dwarf stars will slowly burn out over trillions of years, eventually cooling into dark, dead stellar remnants known as black dwarfs. One by one, the lights of the universe will go out. The cosmos will enter an era known as the degenerate era, populated only by cold, dark, stellar corpses, rogue planets, and wandering black holes. The universe will be a profoundly cold and dark expanse. But even in this unimaginably distant future, the universe will not be dead. The physical matter may have exhausted its thermal and luminous energy, but the underlying structure of reality will remain as active as ever. This is the ultimate consequence of the quantum vacuum. Even when the universe reaches a state of maximum entropy, a state commonly referred to as the Big Freeze, the space itself will not be empty. Because the expansion of the universe is driven by dark energy, and dark energy is an intrinsic property of space, the creation of new volume continuously generates more vacuum energy. The underlying quantum fields will keep humming with the exact same zero-point energy that they possess today. When new space is created, the total energy of the vacuum increases. In classical terms, this appears to violate the first law of thermodynamics, which states that energy cannot be created from nothing. However, in the framework of general relativity, the vacuum possesses a negative pressure. As the universe expands, the expanding volume does work against this negative pressure. The energy required to do this work is exactly equal to the new vacuum energy created within the expanded space. It is a perfectly balanced, self-sustaining thermodynamic loop. The universe expands. The expansion does work against the negative pressure of the void, and that work manifests as more vacuum energy, which in turn accelerates the expansion even further. This loop is the constant pulse of the modern cosmos, an eternal engine running on the fundamental uncertainty of the subatomic world. The virtual particles will continue their eternal cycle of spontaneous birth and immediate annihilation. The electron field, the quark field, and the electromagnetic field will continue to boil. The constant, restless noise of the quantum realm does not depend on the presence of stars, galaxies, or human observers. It is a fundamental requirement of the physical laws that govern existence. The cosmos will remain an infinite, restless ocean of potential, permanently vibrating in the dark long after the last star has faded into absolute zero. We must recognize that the continuous pulse of expansion fundamentally alters the thermodynamic destiny of reality. In classical thermodynamics, a closed system will eventually reach a state of equilibrium, a perfectly balanced stillness where no further work can be done. But an accelerating universe, constantly generating new space and new vacuum energy, defies this simple classical conclusion. It is an open-ended system driven by a microscopic restlessness that cannot be switched off. The realization that the void will outlive the stars forces a profound shift in how we prioritize the components of reality. For centuries, human science has focused primarily on the bright, visible matter of the universe. We studied the planets, we categorized the stars, and we mapped the galaxies. We treated the empty space between them as nothing more than a convenient backdrop, but the physics of the constant pulse reveals that the visible matter is actually the temporary anomaly. The stars and galaxies are just fleeting, localized structures built upon the true, permanent foundation of the cosmos. That foundation is the vibrating vacuum. The emptiness is the main structural component of the universe. It was the microscopic jitter of this vacuum that provided the initial seeds for all cosmic structure during the Big Bang. It is the continuous energy exchange of this vacuum that currently stabilizes the atoms within our biological bodies. And it is the repulsive pressure of this vacuum that will ultimately dictate the final, expanding state of the cosmos. The dark, boiling void dictates the entire physical reality. Yet, even this picture of a cold, expanding but eternally vibrating universe might not be the final chapter. While the constant pulse of dark energy guarantees that space will never completely sleep, it also exposes the universe to a completely different type of existential threat. We have assumed that the baseline zero-point energy of the quantum fields is a permanent, stable condition. We have assumed that the vacuum we inhabit today is the absolute lowest possible energy state the universe can achieve. But modern theoretical physics warns us that this assumption might be a fatal error. The unresting fields that built our reality from subatomic fluctuations might be hiding a catastrophic instability. The universe could be sitting in a precarious, temporary state, waiting for a localized quantum event to completely rewrite the laws of physics across the entire cosmos. To understand this ultimate threat, we must turn our attention away from the expansion of space and look deeply into the stability of the vacuum itself. We must investigate the terrifying concept of the false vacuum and the catastrophic physical implications of vacuum decay. What if the restless void we currently inhabit is merely a temporary, precarious phase, waiting to spontaneously drop into a deeper, destructive state of reality? We have established that the continuous expansion of the cosmos guarantees that space will never completely sleep. The dark energy driven by the quantum vacuum pushes the galaxies apart, creating an eternal engine of vibrating emptiness. However, this perpetual motion exposes the universe to a completely different type of existential threat. We have operated under a massive scientific assumption. We have assumed that the baseline zero-point energy of the quantum fields is a permanent, stable condition. We assumed that the vacuum we inhabit today is the absolute lowest possible energy state the universe can achieve. But modern theoretical physics warns us that this assumption might be a fatal, catastrophic error. To understand this ultimate threat, we must examine the concept of phase transitions and energy states. In the physical sciences, every system naturally seeks its lowest possible energy state, known mathematically as the ground state or the true vacuum. Water naturally flows downhill, and a physical ball will roll down a slope until it rests firmly at the bottom of a valley. Once a system reaches its absolute minimum energy state, it is considered perfectly and permanently stable. It cannot fall any further. For decades, physicists assumed that the empty space of our universe, despite its boiling quantum foam and constant zero-point energy, represented the absolute bottom of the cosmic energy valley. We assumed that the baseline energy driving the expansion of the cosmos was the true, final vacuum. However, the discovery of a highly specific subatomic particle in the year 2012 forced a terrifying re-evaluation of this foundational assumption. At the Large Hadron Collider in Geneva, Switzerland, particle physicists finally confirmed the physical existence of the Higgs boson. The Higgs boson is the physical, observable manifestation of the Higgs field, an invisible, foundational energy field that permeates the entire observable universe. As fundamental particles, such as quarks and electrons, move through the Higgs field, they experience a specific type of subatomic resistance. This resistance is exactly what gives elementary particles their physical mass. Without the continuous presence of the Higgs field, electrons would possess absolutely no mass. They would fly apart at the speed of light, atoms could never form, and the complex chemistry required for biological life would be physically impossible. The specific, baseline value of the Higgs field dictates the exact mass of these fundamental particles, which in turn dictates the laws of chemistry and physics. The stability of our entire macroscopic reality depends entirely on the Higgs field remaining absolutely constant. But when theoretical physicists measured the exact mass of the Higgs boson, coming in at approximately 125 giga-electron-volts, and compared it to the mass of the heaviest known elementary particle, the top quark, the resulting mathematics revealed a highly disturbing pattern. The top quark is incredibly massive, and its exact weight heavily influences the overall stability of the Higgs vacuum. When these two precise experimental values are plugged directly into the equations of the standard model of particle physics, the results indicate that the current energy level of the Higgs field is not actually resting at the absolute bottom of the potential energy valley. Instead, the mathematics strongly indicate that our universe is likely resting in a local depression, a small, shallow dip situated halfway up the side of a much larger theoretical mountain. We are caught in what physicists call a metastable state. This condition is known in quantum mechanics as a false vacuum. It appears completely stable from our localized human perspective because it would require a massive, impossible injection of external energy to push the entire universe out of the small dip and over the surrounding energy barrier. If the universe were governed purely by the rigid rules of classical physics, we would be perfectly safe. A ball resting in a shallow valley will never climb over the surrounding hills unless a physical force acts upon it. But we have already proven that the universe is not classical. It is governed by the chaotic, restless laws of quantum mechanics, and the underlying vacuum is constantly boiling with mathematical uncertainty. In the quantum realm, a subatomic particle does not necessarily need enough kinetic energy to physically climb over an energy barrier. Because of the inherent structural uncertainty in its precise position and energy, a particle possesses a strict mathematical probability of simply passing directly through the solid barrier. This phenomenon is known as quantum tunneling. It is not theoretical. It is a proven physical process that occurs constantly inside the core of our Sun, allowing nuclear fusion to take place at temperatures that would classically be far too low. This exact same quantum tunneling mechanism applies directly to the false vacuum of the Higgs field. At any given moment, in any random coordinate of empty space across the entire observable universe, a random quantum fluctuation could cause the Higgs field to tunnel directly through the energy barrier. A microscopic patch of space would suddenly drop from our current false vacuum state down into the true vacuum state, hitting the absolute final bottom of the cosmic energy valley. If this quantum event were to happen, the physical consequences would be catastrophic, absolute, and completely unavoidable. The transition would immediately create a microscopic bubble of true vacuum. Inside this localized bubble, the energy level of the Higgs field would be fundamentally different. Because the surrounding false vacuum of our universe exists at a much higher unstable energy state, it would be inherently vulnerable to the newly formed true vacuum. Nature abhors an energy imbalance. The microscopic bubble of true vacuum would instantly begin to expand, aggressively consuming the surrounding false vacuum in a violent attempt to stabilize the entire universe. The walls of this rapidly expanding bubble would move outward in all directions at the exact speed of light. Because it expands at the ultimate cosmic speed limit, it would be completely invisible to any observer. We would receive no warning, no precursor radiation, and no signal of our impending doom. The wall of absolute destruction would arrive at the exact same instant as the light that carries its image. As the boundary wall of the true vacuum sweeps through a solar system, a planet, or a human body, it would instantly rewrite the fundamental laws of physics. Because the baseline value of the Higgs field drops inside the bubble, the mass of every elementary particle would violently and permanently change. Electrons would no longer possess the correct mass to maintain their stable orbits around atomic nuclei. The delicate, precise electromagnetic balance that holds complex molecules together would shatter in less than a trillionth of a second. All physical matter, from the dense iron in the core of the Earth to the superheated hydrogen in the center of the Sun, would instantly disintegrate into a chaotic, unrecognizable plasma of altered fundamental particles. The structural integrity of the cosmos would be permanently erased and replaced by a completely alien, hostile, physical reality. This terrifying scenario, known to cosmologists as vacuum decay, is the ultimate physical manifestation of the restless void. While statistical probability suggests that a spontaneous vacuum decay event is exceedingly rare, perhaps not occurring for 10 to the power of 100 years, the timeline is completely irrelevant to the underlying physics. The fundamental truth remains unchanged. We exist in a fragile, temporary equilibrium, balanced precariously on the edge of a subatomic cliff. The exact same microscopic quantum jitters that generated the seeds of the galaxies and breathed physical structure into the universe possess the inherent capability to completely dismantle it. The vacuum is not merely an empty stage, nor is it just an eternal engine of expansion. It is a loaded weapon, continuously humming with the raw, unpredictable potential to end everything in an absolute flash of rewriting light. Our journey through the quantum landscape forces a profound philosophical and scientific transformation in how we view our place in the cosmos. Throughout the entirety of human history, we have viewed space as nothing more than a cold, inert backdrop. We looked up at the night sky and saw a silent, empty stage upon which the grand drama of matter and biological life plays out. We looked at the void and saw an enemy to be feared, an absolute nothingness that represents the ultimate end of existence. We defined ourselves by our physical separation from that empty space. We believed that to be alive, to possess solid physical form, was to be a rare exception in a universe dominated by dead, inactive nothingness. But modern quantum physics has shattered this classical paradigm completely and permanently. We now know, with absolute empirical certainty, that the stage itself is alive. We are not isolated, lonely observers traveling across a dead and empty desert. We are passengers swimming within a dynamic, infinitely complex, and eternally vibrating sea of energy. The universe is fundamentally and mathematically incapable of ever falling asleep. Its constant, silent pulse built the stars, shaped the galaxies, and continues to drive the accelerating expansion of physical reality. When you look at your own hands, when you feel the solid ground beneath your feet, you must realize that you are feeling the direct physical result of a microscopic storm. The atoms in your body are stabilized by the ceaseless borrowing and repayment of energy from the quantum vacuum. The electrons orbiting your atomic nuclei are shielded by clouds of virtual particles that flash into existence for a trillionth of a second before annihilating back into the void. You are not separate from the nothingness. You are an intricate, highly organized extension of it. The solid matter that constructs our world is merely a localized, dense vibration resting upon the infinite ocean of the underlying quantum fields. Furthermore, the grand architecture of the entire observable universe is a direct monument to the restlessness of this void. The majestic galaxy clusters, the glowing cosmic filaments, and the vast dark matter halos are all the physical descendants of microscopic subatomic jitters. When the universe was smaller than a single proton, the fundamental fields could not remain still. They were forced, by the uncertainty principle, to fluctuate, and when cosmic inflation grabbed those microscopic fluctuations and stretched them across billions of light-years, it froze the noise of the subatomic realm into the macroscopic map of the cosmos. Every star that shines in the night sky is a physical testament to the fact that the universe was structurally forbidden from being perfect and smooth. However, as we have discovered, this eternal restlessness carries a terrifying existential weight. The exact same vacuum that birthed the physical universe and stabilizes the chemistry of life currently threatens to tear the cosmos apart. The continuous creation of new space generates more dark energy, pushing the galaxies further and further away from one another. Eventually, this repulsive force will isolate every galaxy, leaving the universe cold, dark, and unimaginably lonely. And lurking beneath that slow, inevitable expansion is the sudden, catastrophic threat of vacuum decay. The realization that our universe might be resting in a false vacuum, a temporary and unstable energy state, means that our reality is inherently fragile. At any moment, a random quantum fluctuation could cause a microscopic patch of space to tunnel through the energy barrier, dropping into the true vacuum. The resulting bubble of absolute destruction would expand outward at the speed of light, instantly rewriting the laws of physics and vaporizing all matter in its path. We exist on the edge of a subatomic knife, balanced only by the temporary mathematical parameters of the Higgs field. This dual nature of the quantum vacuum, as both the ultimate creator and the potential ultimate destroyer, demands a completely new perspective on our existence. We are a rare, fleeting phenomenon. Biological life, with its complex consciousness and ability to observe the universe, is a miraculous byproduct of these precise, restless quantum conditions. We are the universe experiencing itself, built from the very energy fluctuations that prevent the cosmos from falling silent. Our ability to build space telescopes, to map the cosmic microwave background, and to smash particles together in giant accelerators is nothing less than the vacuum developing the capacity to look back upon its own boiling surface. We must completely abandon the comforting illusion of the quiet void. The emptiness of space is the most powerful, active, and dominant force in existence. It is the ultimate cosmic bank, offering infinite loans of energy to construct physical matter. It is the ultimate sculptor, providing the initial blueprints for gravity to build the massive cosmic web. And it is the ultimate destroyer, driving the runaway acceleration of dark energy and harboring the potential for instantaneous, light-speed physical collapse. We have seen how the unresting quantum fields built our reality from subatomic whispers. We have explored the Casimir effect, the boiling quantum foam, and the massive discrepancy of the vacuum catastrophe. But as we just explored, this same vacuum might be hiding a catastrophic instability, a false vacuum ready to collapse and rewrite the laws of nature at any second. The concept of vacuum decay is not a piece of science fiction. It is a rigid mathematical probability embedded directly into the standard model of particle physics.